Hello dear students, I am Praveen, your chemistry educator. Students, in today's video, what we are going to discuss, the chapter haloalkanes and haloarenes completely for the NEET examination. So overall, if I talk about the content part, so we will be discussing about all the reactions, all the concepts we have in this chapter, that means haloalkanes, haloarenes. But apart from that, I will also guide you that how you can study the whole organic chemistry with ease, right? So there are certain tricks, right? Certain methods which if you follow, so the organic chemistry will become much more easier, much more convenient for you. So along with this chapter, I will also guide you through your organic chemistry, right? And of course, after completing this video completely, see, in the organic chemistry part, never skip any single concept, because most of the time in organic, the concepts, the questions will be asked in such a manner where you will require 2, 3, 4, 5, 6 concepts connected together. So focus on each and every topic in your organic chemistry in every chapter, right? So watch this video completely, take your notes, note everything, whatever I will be teaching in this session. And then after completing this session, we are providing the DPPs in the video description. So your task will be to practice all the questions that we are providing in the DPP in the description. And also those DPPs you can get on the PW app. So download the PW app. From there, you can get the DPPs not only for this chapter, but for the rest chapter of chemistry and for different subjects also. So you can start your journey with PW just like lakhs of students are doing with us. So now let's start today's session with the very first point, that is what we are going to discuss, right? What are the contents, what are the topics that we are going to discuss in this session? So in the haloalkanes, haloarenes chapter, students, first thing is we will talk about the introduction of the chapter, right? And the classification of halogen containing compounds, right? Then we will move into the alkyl halide part, where we will discuss how you can do the preparation of alkyl halide and the physical properties like mainly boiling point, right? Physical state, melting point. Then we will discuss the chemical reactions, the chemical properties of alkyl halide like SN reaction, then elimination reaction, and then reaction with metals for the alkyl halide. And after doing the preparation of alkyl halide and reactions of alkyl halide, then we will go into the haloarenes part, where again we will talk about the preparations of haloarenes, how you can prepare your haloarenes, and then the reactions of haloarenes, right? And in reaction of haloarenes, we will talk about electrophilic substitution reaction or electrophilic aromatic substitution reaction, you can also say. Then the SN reactions of haloarenes, and again reaction of haloarenes with metal. And finally, we will see some of the examples of polyhalogen compounds and their usage, right? So now, when you talk about haloalkanes, haloarenes, so you can say in general, right? Sometimes this chapter is also called as halogen containing compounds, right? So you can say that here we are going to discuss about those organic compounds which contains halogen. Now first thing is, you should know these points, right? First thing is, in our life, if I talk about where we can observe, where we can get, where we use, right? Practically in our daily life, right? The compounds having halogen. So I have some of the examples, like if you talk about the compound chloroamphenicol, right? So this is a medicine which is used, right, for the treatment of typhoid fever, right? Then similarly, if you talk about thyroxine, so thyroxine is the compound, right, whose deficiency will cause goiter, right? And then we have another very famous compound, chloroquine, which is used for the treatment of malaria, the disease malaria. So some of the compounds of haloalkanes, haloarenes, right, or halogen containing compounds, their application, their usage known, right? At least these 2-3 common compounds like chloroamphenicol, thyroxine, and chloroquine, you should know, right, that what are the uses of these compounds. Now again, coming back to the main part of the chapter, right? The first thing is, we have to classify, we have to learn the classification of halogen containing compound, right? So according to different ways, we have done the classification. The first thing is, the first way is on the basis of degree. I hope you know degree of carbon especially, degree of alpha carbon especially from your basic organic chemistry chapter itself, right? From class 11th, right? Degree means what? The number of carbon attached with any particular carbon. So according to degree, what we do, we classify the halogen containing compounds into three categories. One is primary, which is also called as 1 degree alkyl halide. The other one is secondary, which is also called as 2 degree alkyl halide, right? And then finally we have tertiary, which is called as 3 degree alkyl halide. Now when I say 3 degree or tertiary alkyl halide, right, so that means the carbon from which your functional group is attached, that means halogen. So from that carbon, 3 other carbons will be attached, right? So here you can say that this is a alpha carbon, this is your alpha carbon. Generally in your compound, right, the carbon from which the functional group is attached, so that carbon is called as alpha carbon. So in this case, with your alpha carbon, total 3 carbons are attached, right? So this alpha carbon is 3 degree, right? So overall this compound is called as tertiary halide, right? In the same way, if you notice, in this case, this is my alpha carbon by which the halogen is attached, and in this case the alpha carbon is 2 degree because with alpha carbon 2 carbons are attached and the third one is hydrogen here, right? So if your alpha carbon is 2 degree, right, it will be called as 2 degree or secondary halide. And in the same way, with your alpha carbon, the carbon from which halogen is attached, if only one carbon is attached and rest 2 are hydrogen, then your alpha carbon is what? Alpha carbon is 1 degree. So in that case, you can say that it is a 1 degree or primary halide. So according to degree, we can classify halogen containing compounds as primary, secondary, tertiary, or 1 degree, 2 degree and 3 degree, right? So this is a classification point on the basis of degree. Now, the next classification we have for the halogen containing compound is based on how many halogens you have in your compound, right? Whether you have only one halogen atom in your compound per molecule, or whether you have 2 halogen, 3 halogen. So on that basis, what we say that if a compound has only one halogen, if your compound has only one halogen, then it is called monohaloalkane, right? If your compound has 2 halogens, then it is called as dihaloalkane, right? And of course, you will say alkane when the carbon chain will have only single bond. But suppose that if your carbon chain has double bond and triple bond, then you can say that will be dihaloalkene or dihaloalkyne, right? But point is, we can say that one halogen means monohalo compound, 2 halogens means it is a dihalo compound, and if you have 3 halogen, then it is called trihalo. In the same way, you can have tetrahalo, polyhalo compounds also. So I hope you have understood. On the basis of number of halogens also, we classify the halogen containing compound as monohalo, dihalo, trihalo and so on, right? Now here, if you observe about the dihalo compounds, so in the dihalo compound, we have a very important classification here further. Students, the dihalo compounds can be further classified as geminal dihalide and vicinal dihalide. You know what? Geminal dihalide means when your halogens, when both of the halogens are attached on the same carbon. When both the halogens are attached on the same carbon, then it is called as geminal dihalide. But suppose if both halogens, they are attached on the adjacent carbon, right? So then it will be called as vicinal dihalide. So halogens present on the same carbon, it will be called geminal, and halogens present on the adjacent carbon, it will be called as vicinal, right? You can see that here we have written some of the common names, right? Like for this compound, for this example, CH3CHCl2, its common name is ethylene chloride. And for this compound, that means CH2CH2Cl, its common name is ethylene dichloride. I hope that you people have no issues regarding the IUPAC nomenclature, because you must have learned that IUPAC nomenclature in your basic organic chemistry chapter, right? For this compound, common name is ethylene dichloride, but its IUPAC name will be 1,2-dichloroethane, right? Similarly, for this compound CH3CHCl2, the common name is ethylene chloride, right? But its IUPAC name will be, students, 1,1-dichloroethane, right? But overall, we need to understand that apart from degree, right, Halogen containing compounds are also classified on the basis of how many halogen they have, right? And finally, the third classification is one of the important classification for you, because from here sometimes you get direct questions in the examination. It is based on the hybridization of your alpha carbon. Students, halogen containing compounds, right, on the basis of hybridization of alpha carbon can be classified into two parts, right? You will have some of the compounds in which the alpha carbon will be sp3 hybridized. Means what? Means in your halogen containing compound, your alpha carbon will be sp3 hybridized. On the other side, there will be some halogen containing compounds in which the alpha carbon will be sp2 hybridized. So two types. In one case, the alpha carbon is sp3 hybridized. In other case, the alpha carbon is sp2 hybridized. Now we have some of the examples of these two. Like if you talk about sp3 hybridized alpha carbon, so in that part we have three types of halogen containing compound. One is normal alkyl halide or alkylic halide. One is normal. Normal means there will be carbon chains in it, right? Only single bonds in it, right? And alpha carbon will be sp3, right? And for alkyl halide, for general normal alkyl halide, right, you can say that representation will be something like this, Rx. For example, if I take this compound, CS3, CH2, Br. So in this what? This is a simple carbon chain, right, in which the alpha carbon, which is sp3 hybridized. So this CH3CH2Br will be called as normal alkyl halide, right? And you can write its general formula also. The general formula of general alkyl halide will be CnH2n plus 1x, right? But apart from this alkyl halide, we have another one which is called benzyl halide. Now students, in benzyl halide, the alpha carbon will be sp3 hybridized. The alpha carbon will be sp3 hybridized. But with your alpha carbon, right, or the carbon from which halogen is attached, a phenyl group, a benzene ring will be attached, right? So if you have a compound in which the alpha carbon is sp3, and on the alpha carbon, of course, you have halogen, but on the alpha carbon, a benzene ring is attached. So then it is classified as benzyl halide, right? One more we have in the sp3 part, which is called allyl halide, Let me write it here. Allyl. In case of allyl, what will happen? Again, the alpha carbon will be sp3, right? But here, the beta carbon will be sp2 hybridized. So the carbon from which halogen is attached, it is sp3, but the carbon just next to it will be sp2 hybridized, right? So if you have a structure like this in which alpha carbon is sp3, but the next carbon, which is also called as beta carbon, if it is sp2 hybridized, then this is called as allyl halide. So these classifications are very important for you: alkyl halide, benzyl halide, and of course allyl halide. Now talking about, right, those cases in which your alpha carbon is directly sp2 hybridized. So we have two examples for those types of compound also. One is vinyl halide. In case of vinyl halide, what will happen? Directly, the carbon from which halogen is attached, it will be sp2 hybridized. It will be sp2 hybridized, right? It can be open chain, it can be cyclic, but it should not be aromatic, because if your halogen is attached with aromatic, then it is called as aryl halide. Like suppose you take a benzene ring, which is an aromatic compound, and in your benzene ring, you remove one of the hydrogen and you attach a halogen here. So now in this case also, the alpha carbon is sp2 hybridized, but here it will not be called as vinyl halide, it will be called as aryl halide, right? So these two are the cases, vinyl halides and aryl halides, in which the alpha carbon is directly sp2, right? So these five classification, right, benzyl, allyl, alkyl, aryl and vinyl you should know very well, because you get direct question in the examination, students. Right? So now we have understood the classification very well. So let's quickly move on to the next point, that will be the preparation of alkyl halide. So we are starting with the preparation of alkyl halide, but I told you I will tell you something interesting for your organic chemistry, right? So before I begin with the preparations of alkyl halide, students, let me tell you one thing. Suppose if you are studying the organic chemistry for the first time, so then you can do like this preparation and reaction and so on, just like it is given in your NCERT or in your books. But when you are revising the organic chemistry at least, so there, do not study like preparation and reaction, right? Only focus on the chemical reactions of each and every compound. You know what? The whole organic chemistry you can study like this, right? Take your homologous series, take your compounds like alkane, alkene, alkyne, benzene, alkyl halide, aryl halide, alcohol, ether, phenol, aldehyde, ketone, acid, amine, nitro, cyanide. Take all those compounds and one by one just focus on their chemical reactions, right? If you study all the chemical reactions of all these compounds, right, believe me, you don't have to study, you don't have to go into the preparation part, because preparations are always a repeated thing in the organic chemistry. Like suppose here also I am talking about the preparation of alkyl halide, but somewhere, right, when I will be preparing alkyl halide, I will be using alcohol here. So whatever reaction I will be teaching you here in the preparation of alkyl halide, this same reaction you can also find in the alcohol chapter, where under the topic chemical properties of alcohol. So point is, the chemical property of alcohol, or one of the chemical property of alcohol, right, the same reaction here we are going to discuss as preparation of alkyl halide. So 90% of the preparation reactions, they are just a repetition, right? They are just a repeat of your reaction part. So for all the compounds, if you study only the reaction part and then of course you complete all the name reactions, you are done with your organic. You don't have to go into those preparation part, right? But again, because here we are doing everything in one shot, so we have to cover all these points, preparation and reaction. So here I will be discussing preparation. But when you are revising by your own, just go into the reaction part for each and every compound, for each and organic chapter. So now let's start, right? The first preparation of alkyl halide is from alcohol, and from alcohol, it is one of the major preparation method of alkyl halide, because from alcohol you have different techniques. Like one is using HCl, then one is using PCl3, PCl5, then one is using SOCl2 and so on. So one by one we will be discussing all those, right? But point is, overall if you see, if you have a alcohol, students, and you treat that with HCl in the presence of ZnCl2 catalyst. So this catalyst requirement is not mandatory, right? You will see very soon that when your alcohol is 3 degree, 2 degree, then you don't require this ZnCl2 catalyst, right? But when your alcohol is of 1 degree, right, in that case you need that ZnCl2 catalyst. But first of all, if I overall write down the general reaction by which you convert alcohol into alkyl halide, so the general reaction can be written something like this. I have some alcohol, I have treated that with HCl, right, in the presence or absence of ZnCl2 depending upon the degree of alcohol. So it will give you alkyl chloride along with the byproduct H2O. Now, my point is, whenever you are studying organic reaction, right, so always focus on what type of reaction it is, right? In your GOC, in your basic organic, you must have seen that organic reactions can be classified, right, mainly into 5 categories, right? One is addition reaction, one is substitution reaction, one is elimination reaction, one is oxidation, one is reduction. So out of those 5, whenever you are doing a reaction, so focus and try to evaluate which type of reaction you are dealing with. Like here, of course, we are converting alcohol into alkyl halide, but this is a type of substitution reaction. Students, if you notice, in this reaction overall, this OH group is getting substituted, and in place of OH, finally we are getting chlorine. Now, if you go into more details, you will very clearly see that, it is a nucleophilic substitution reaction, because in the substitution part also, we have further types, right? Nucleophilic substitution, electrophilic substitution, and radical substitution. So this is a clearly nucleophilic substitution reaction. And in this chapter, this particular topic is very important for us, nucleophilic substitution reaction, because the same concept we will be discussing in the preparation, and the same nucleophilic substitution reaction we will see for alkyl halide in the reaction part. So overall, this is a nucleophilic substitution reaction, right, where ROH or the OH minus nucleophile is getting substituted by the chloride nucleophile. Now, quickly talking about its mechanism, because especially for the nucleophilic substitution reaction, you should know the mechanism very well, right, that whether it is SN1 or SN2, right. I will tell you in this chapter only, in today's video only, that what is the meaning of SN1, what is the meaning of SN2 in detail, right. I will also tell you all those conditions for SN1, SN2. But overall, try to understand that this is one of the example of SN reaction of alcohol. Now, how this reaction occurs, please notice carefully, which you also say that it is called reaction mechanism. So let's discuss about the reaction mechanism now. In this reaction, students, what will happen? Your substrate is alcohol. Okay, one more point. Whenever you are doing a reaction or whenever you are analyzing a reaction, so first always focus on the catalyst, then on the reagent, and then on the substrate. If you have the knowledge, if you know the properties of catalyst, reagent, and substrate, you can easily do the reaction, right? So in this case, our reagent is HCl, right? Now, do we know HCl? I hope very well. We know very well that HCl is an ionic compound, right? It is an electrolyte, and we know that electrolytes, they will decompose into cation and ion. So first, if I focus on my reagent HCl, I can say that it is an electrolyte and it will dissociate into H plus and Cl minus ion, correct? Now, I understood what is my reagent. I got that I will be getting H plus and Cl minus from this reagent. Now go and focus on the substrate. Your substrate is alcohol. And students, please always remember that alcohol always acts as a nucleophile. If you consider alcohol like a reagent, then alcohol always acts as nucleophile. Why? Because in alcohol, the central atom oxygen, it has two lone pairs, and out of those two lone pairs, it can easily share one of its electron pair. So from today onwards, remember like this, that all alcohol always try to give electron to others. If I am alcohol, so what will be my tendency? My tendency will be to always donate my electron from the oxygen atom to the others, right? And to the other means electrophile. So here, if you notice, this oxygen has tendency to donate electron, and the electron deficient particle out of these two is H plus. So from here, your reaction will begin, right? How? That oxygen will give its lone pair, or it will share its lone pair with the H plus ion. This is your first step. So you can say that it is called protonation. This step is called protonation. Now after protonation, you will get this kind of structure, RO, H, one lone pair, H, and now this oxygen will have positive charge. Definitely it will have positive charge. Why? Because it is donating electron, just like a coordinate bond. So it will have plus charge, it will have minus charge. Because this hydrogen has initially plus charge, and now due to bond formation it is getting minus charge. So plus minus, this hydrogen overall will become neutral. Now definitely you can understand that this species, it is not stable, right? It is not stable, right? So from here you will have elimination of water, you will have dehydration, right? So this RO bond here, it will break, and always remember that water is a very good leaving group. there are certain compounds which we always say that they are very good leaving group in the organic chemistry, like water, CO2, N2, salts, right? So from here, H2O will go out, and as soon as you remove H2O from this R means somewhere you have some carbon chain here. So from carbon, if you remove this H2O part, you will get a carbocation intermediate, right? So you will get a carbocation intermediate here. But again, always remember that you will get carbocation depending on the degree of alcohol, right? Suppose here for your alcohol, right? Let me write it here. Here for your alcohol, if it is 2 degree or 3 degree, in that case, you will easily get the carbocation. But again, if your alcohol is 1 degree, so in that case, you won't get carbocation because 1 degree or 0 degree carbocations, they are unstable. So if your alcohol is 2 degree or 3 degree, right, dehydration will take place and you will get a carbocation intermediate. And I hope you know very well that whenever we get carbocation intermediate in any organic reaction, so there is a possibility of rearrangement, right? Hydride shift, methyl shift, ring expansion. So those things can happen here, right? So after getting carbocation, if possible, you can do your rearrangements, whatever possible, right? And if no rearrangement is possible, then whatever carbocation you get, it will directly react with your nucleophile part, right? So we started with this H plus, and now finally this nucleophile Cl minus, it will come, it will attack on this carbocation, and you will be getting your RCl, that means your alkyl chloride, right? So currently I have not told you what is SN1, SN2, but very soon you are going to see one thing, that in a nucleophilic substitution reaction, if we get carbocation intermediate, then it is SN1 mechanism. That is called SN1 mechanism. And if you don't get carbocation, then probably it will be SN2 mechanism. Like here, when you take 2 degree, 3 degree alcohol, so in that case you get carbocation, so it is following SN1 mechanism. But if you take 1 degree alcohol, students, if you take primary alcohol, in that case, the mechanism will not be SN1, but it will be SN2. That will be SN2. So overall, till now I have told you 2 points. 1, what is this reaction? And 2, how this reaction takes place. Correct? Now, there are few points from which we get questions again, right? Sometimes we get questions related to reactivity. Like here, your reagent is HCl, which is of course, halo acid, right? So you can have different halo acids, like you can have HF, you can have HCl, you can have HBr, you can have HI. So all these halo acids can be used here, but there will be difference in the reactivity. Out of these halo acids, if you notice, the most reactive one will be HI, then HBr, then HCl, then HF. Why? Because you have clearly seen that for this reaction, we need the dissociation of this HCl into H plus and Cl minus. And the dissociation is easiest for HI, because in HI, the bond length is large and the bond strength is low. So because HI has weak bond, it can easily decompose into H plus and I minus, right? So reactivity will be highest for HI, then HBr, then HCl, then HF. So this is a point, right? That means reactivity according to the different reagent. Now, again, here reactivity can be compared on the basis of your substrate. So these are some of the generalized points, students. Not only in this reaction, like whenever you are dealing with a reaction, you have reagent, you have substrate. So in that particular reaction, there can be a comparison of reactivity on the basis of different reagents as well as different substrate. So on the basis of reagent, you understood that HI is most reactive and HF is least reactive. Now talking about your substrate, if you take different alcohols, like if you take 1 degree alcohol, then if you take 2 degree alcohol, students, if you take 2 degree alcohol, and if you take 3 degree alcohol, so out of these 3 alcohol, right, I can clearly say that out of 1 degree, 2 degree, 3 degree alcohol, the most reactive one here with your halo acid will be 3 degree, because in case of 3 degree, we can get the most stable carbocation. And then it will be 2 degree, and then it will be 1 degree. So that's the reactivity order, right, of alcohol with halo acid. Most reactive 3 degree, then 2 degree, then 1 degree. Not only that, in your alcohol chapter, you will see that this particular reaction is also used as test of alcohol. We call it Lucas test. We call it Lucas test, right? It's important again. Lucas test is very, very important. Not in this chapter, but in your alcohol chapter, right? In Lucas test, what happens? The HCl and ZnCl2 combo, right? You take concentrated HCl and anhydrous ZnCl2. So this concentrated HCl and anhydrous ZnCl2, right? This is called as Lucas reagent. And this reagent we use to determine degrees of alcohol. Why? Because when you take 3 degree, you know that here 3 degree alcohol is most reactive. So this will react immediately in the Lucas test. Within seconds, right, you observe turbidity when you react 3 degree alcohol with Lucas reagent. And if you take 2 degree alcohol, so 2 degree alcohol is comparatively less reactive, so it will take more time, right? It takes around 3 to 4 minutes to show turbidity. And if you take 1 degree alcohol, in that case, you require heat. You require certain amount of heat. At normal temperature, 1 degree alcohol will not give immediate or turbidity after 3 to 5 minutes. So in 1 degree alcohol, you require heat to get the turbidity. And from this, we can easily estimate that whether, we can easily detect that whether your alcohol is 1 degree, 2 degree or 3 degree, right? So I just covered this point, but this Lucas test you have to see in your alcohol chapter. But now I hope you have understood very well about this particular reaction of alcohol with HCl and ZnCl2, and of course its mechanism and reactivity. Now from the alcohol only, we have other reagents by which you can prepare alkyl halide. But one more point I will have to add here, I should add here. Sometimes students, what will happen, this reagent will not given like this. They will not directly give you HX. Instead of HX, sometimes they can give you a combination of salt and acid, right? Like instead of giving HBr, they can write it like this: NaBr plus H2SO4. So you need to understand here that instead of HBr, if I give NaBr and H2SO4, so this will produce HBr. From NaBr you will be getting Br minus, and from H2SO4 you will be getting H plus. So indirectly, NaBr H2SO4 is nothing but your HBr, right? So it will have the same reaction. And sometimes you will see this Ki with H3PO4. So you can treat Ki and H3PO4 just like Hi, So do not get confused by looking at these reagents like NaBr H2SO4 with alcohol or Ki H3PO4 with alcohol. They will function same like HBr and Hi. HBr or Hi. Correct? So now we are done with the first preparation, that is alcohol and HCl. So now let's talk about the second reaction, which is reaction of alcohol with PCl3 and PCl5. So there are two reactions, but we have written them together because their mechanism, their concept is quite similar. First thing is, when you treat alcohol, students, when you treat alcohol with PCl3 or PCl5, again it is a SN reaction. Again it is a SN reaction. Your alcohol, right, it will react with PCl3 to produce RCl, and because at a time 3 moles of alcohol will react with PCl3, so in the byproduct you will be getting H3PO3. So one by one here what happens, this OH is getting replaced by this chloride, right, and this chloride is getting replaced by that OH minus hydroxide. So overall, if you notice, in this also, this OH minus is getting substituted by the chloride ion. So it is also SN reaction. It is also SN reaction, right? Okay. With alcohol HCl, you noticed that it is most of the time SN1. Similarly, alcohol, when it reacts with PCl3 or PCl5, so here most of the time it follows SN2 mechanism, especially if your alcohol is 1 degree or 2 degree. Right, so whether it is 1 degree or 2 degree alcohol, in both the cases, right, it follows SN2 mechanism, right? So one example, one preparation we saw, right, from SN1, and now the second preparation we are looking, it is an example of SN2. So in the preparation part itself, right, we have the concept of SN1 and SN2 reactions. So here again you have to focus first on the reagent part, right? So in this case, our reagent is PCl3. Right, now what is the structure of PCl3? Of course, it is not electrolyte, and if you look at the structure, so in PCl3, the phosphorus is attached with 3 covalent bonds with the chlorine. Now, if you see the polarity, students, so in this, out of the phosphorus and chlorine, phosphorus is less electronegative, so it will have some delta positive charge, and all the chlorines, it will have some delta negative charge. Now, you know what? From polarity, we get an idea that which atom can act as electrophile, which atom can act as nucleophile. In this PCl3, if you notice, this phosphorus will act as electron deficient atom, and these chlorines, they will act as electron rich particle, electron rich atom, right? So in this PCl3, what we know that phosphorus is electron deficient and chlorine is electron rich. Now, if you talk about the substrate, so here your substrate, again it is alcohol. Just now in the previous reaction, I told you that alcohol, right, it has tendency to donate electron. So here also your alcohol will try to donate electron, and when it will donate electron, when it will share electron through coordinate bond, so in PCl3, the phosphorus atom will accept electron, right? And that's how this reaction will proceed. This electron pair will be shared with the phosphorus atom. So initially you will be getting this type of unstable species ROH plus, right? Then it is attached with phosphorus now, Cl, Cl, Cl minus. Of course, it is unstable. Now here, if you notice, the phosphorus, it has 4 bonds and a negative charge. So from this, chlorine will go out, right, in order to make the phosphorus stable, right? In order to make the bonds of phosphorus again 3. Initially phosphorus had 3 bonds. So again after when your chlorine will leave here, when your chloride will go out from here, the phosphorus will become neutral and again it will have 3 bonds. So after chlorine, when it goes out, now your structure will be something like this. ROH plus a lone pair, of course, on oxygen, P, and now this phosphorus will have 2 chlorine, and this chloride, now it is outside in your medium. It is outside from the substrate and now it is present in your medium. And you should know that chloride is a nucleophile. So what this chloride will do now, it will go and it will attack on the alpha carbon. It will attack on that carbon from where your oxygen is attached. But point is, in this case, we are not getting a carbocation, right? Directly this chloride is attacking. So here you will always have a backside attack. So if you analyze this reaction according to its stereochemistry in 3 dimension, if you analyze, so what will happen here, if this is your carbon and suppose that above the plane, from here you have your oxygen, phosphorus and 2 chlorine, right? So if this part, oxygen, phosphorus, chlorine, hydrogen, this part is present on the above of the plane, so then your chloride will attack from below of the plane, right? Because it is following SN2 mechanism here. Because it is following SN2 mechanism here. In SN2 mechanism, we always have a back attack, right? Suppose if you have a chiral carbon here, if you have a chiral center here, right? So in that case, the configuration of that carbon will change. The configuration of the carbon will change, right? It will have inversion. But overall, if you notice, when this chloride will attack from backside, this bond will shift on oxygen and now your oxygen will be neutral. So one side you will be getting RCl, and with that in the byproduct you will have POH and you will have 2 chlorine. Right? Now suppose the same step if it repeats 2 times more. Right? So one by one these chlorines, they will go out, and instead of chlorine, one by one you will be having one OH here, one OH here. So overall, that's why we are saying that in this reaction, 3 alcohol molecule will react with 1 molecule of PCl3 to produce again 3 molecules of alkyl chloride along with H3PO3. Along with H3PO3. So H3PO3 is your byproduct. Sometimes in the exam, they will ask the byproducts. So with PCl3, you get what? H3PO3. And not only this, we can generalize this reaction for other halogens also. Instead of PCl3, I can say that here my reaction is with PX3. My reaction is with PX3. Sometimes, instead of writing PX3, they will simply write like this: phosphorus and halogen. So again, please do not get confused. Do not get confused. Because phosphorus H2, when they will react, they will produce this PX3. They will produce this PX3, and again that PX3 here can react in the same fashion, in the same mechanism. Right? So from this, you can produce alkyl chloride, alkyl bromide, alkyl iodide by using different PX3. PCl3, PBr3, right? Pi3 or red phosphorus with Br2, red phosphorus with I2. But point is, this is again a SN reaction which follows kind of SN2 mechanism, especially if your alcohol is 1 degree or 2 degree, right? So I think you have understood now the reaction of alcohol with PCl3. Now students, with PCl5 also, you have the same mechanism, exactly same mechanism. When you take alcohol, you react with PCl5. So now I am not writing the mechanism of this because you can understand by your own. Again, this oxygen will attack on the phosphorus, right? One chloride will go out, that will do back attack, right? And finally, you will be getting what? RCl along with POCl3 and HCl. So in this case, 3 molecules of alcohol will not react. Only 1 molecule will react with 1 molecule of PCl3, right? The byproduct will change. In this case, you will be getting your alkyl chloride, but with this, your byproduct will be POCl3 and HCl. So with PCl3, we were getting H3PO3, and with PCl5 or in general PX5, we get what? POCl3 or in general POX3, right? So this is the second method of preparation of alkyl halide from alcohol itself. One was alcohol plus HCl, and now alcohol with PX3 or PX5. So here, when we prepare alkyl halide from alcohol, right, using another reagent, that is SOCl2, so this reaction is very, very important for us. Why? Because there are 2-3 points in this reaction. First point is, when you prepare alkyl halide from SOCl2, so this reaction is called as Darzin's process. This is called Darzin's process, right? And another point is, it is considered as the best method of preparation of alkyl halide. Why? Because in this you get purest alkyl halide, because the byproducts in this reaction, they are gaseous compound and they can be easily eliminated. So using this alcohol SOCl2, we can obtain the purest alkyl halide. That's why it is called as best method, and it is also named as Darzin's process. Now overall, if you look at the reaction, in this case what will happen? Again, alcohol, it will react with SOCl2, right, to produce RCl, alkyl chloride, and in this case the byproducts will be SO2 and HCl. So you can notice that HCl is a gas and sulfur dioxide is a gas. So these two can be easily removed and we get the pure alkyl chloride. Now, talking about its mechanism, you know what? Once we saw SN1, then the second reaction we saw SN2, and now this reaction has some different mechanism. Students, this reaction follows SNI mechanism, whose full form is substitution of nucleophile internally, and it is completely different from your SN1 and SN2. In this case, you know what will happen? Again, if you focus on the reagent first, so reagent is SOCl2. If you see the polarity, you can easily understand that in this case sulfur has some partial positive charge. So sulfur atom will be acting as electron deficient species, while the oxygen or chlorines, they can act as electron rich species. And your substrate here, reagent is SOCl2 and your substrate is ROH, right? I don't think that now I will have to tell you that alcohol acts as electron donating species, right? Because oxygen has lone pair. So again in this reaction also what will happen? This lone pair will attack on the delta positive charge, that is sulfur atom, and with that here simultaneously this pi bond will break to maintain the valency of sulfur, and this hydrogen, you know that later on it is removed. So this hydrogen will be removed from this oxygen and it will go at this oxygen. So you will be getting this type of unstable species like RO, lone pair, sulfur, chlorine, single bond, oxygen, and this oxygen will grab this H plus, so it will become OH, right? Now point is, in this case if you notice, like in the PCl3 PCl5 reaction, let me show you once. In the PCl3 PCl5 reaction, what was happening? One of the chloride ion, it was going out from this phosphorus, right? And then from outside, this chloride ion was attacking on the carbon, on the alpha carbon. But when you take SOCl2, so in this case, what is happening, right? Out of these two chloride, none of them are going out. So you don't have a free nucleophile here. You don't have a nucleophile which can attack from outside, right? So internally here nucleophile will attack, right? Suppose that if I consider a carbon here and these oxygen sulfur, this is your oxygen, this is your sulfur, right? OH, chlorine. So all of these particles, these atoms will be on the same side in 3 dimension. So internally here, this chlorine or chloride will attack on your alpha carbon, right? And simultaneously this oxygen will go out, right? So one side you will be getting RCl and on the other side you will be getting SO, OH, Cl. And of course this chloride is going out from sulfur, so sulfur will have some positive charge, and this bond pair is going on oxygen, so oxygen will have negative charge, right? This will decompose into SO2 and HCl. You can see that clearly. If you stabilize it, it will convert into SO2 and HCl. And the main product here will be RCl. But point is this, in this case, in this species, nucleophile is not coming from outside, right? Internally, we have nucleophile here and that is attacking on the carbon. So in this case, students, what will happen? Retention will take place. Means in case of SN2, right, the upcoming nucleophile was attacking from the back side. But in this case, what will happen? Because your nucleophile is present internally, so it will attack on the same side where your oxygen is present. So if you observe this reaction, right, stereochemistry wise in 3 dimension, what will happen here? You can say like this. If your alcohol group is present, right, above the plane, I hope you know that outside or above the plane we represent by solid wedge, and below the plane or behind the plane we represent by dashed wedge, right? So if your alcohol OH group is initially above the plane, then in the product side also the chlorine will be above the plane. That means in this case retention of configuration will happen, or in 3 dimension you can say like this, right, that if your OH was initially above the plane, then your chlorine will be also above the plane, and if initially your OH was below the plane, then the upcoming chlorine will be also below the plane, right? And that's why it is called SNI mechanism, because in this case we are not getting a nucleophile from outside which is attacking your carbon like PCl3 or PCl5, right? So in this case, you will have retention. But point is this, for Darjan's process, we have a modification here. You know what, students? In this reaction, in the same reaction, if you take alcohol SOCl2 and you just add a catalyst, that means pyridine. So in the presence of pyridine, now the mechanism will not be SNI, it will be SN2. And in this case, inversion will happen. Like here, if your OH is above the plane, then the chlorine in the product side will be below the plane. Of course, the byproducts will be same, but we will have a little bit difference in the mechanism, right? Now, in this case with pyridine, why inversion is happening, right? Because if you go back and if you see this structure carefully, students, pyridine is a base. So when you will be adding pyridine, what pyridine will do? Pyridine will remove this H plus. Pyridine will remove this H plus. And the OH bond here, it will move towards your sulfur. And when your OH bond, it will move towards sulfur, it will release a chloride, right? So you will have a chloride ion, right, outside of this species in your medium, and that chloride ion, just like your PCl3, PCl5, will attack on the carbon, on the alpha carbon. And again, because your chloride ion is free in that case, in the presence of pyridine, so it will attack from the back side and it will cause inversion of configuration. And that's why then your mechanism will be called SN2. So that's why this reaction is very, very important, right? You know what? It has a name, Darjan's process. It gives you the purest alkyl chloride, right? Without pyridine, it follows SNI mechanism and it follows retention of configuration. But with pyridine, it follows SN2 mechanism with inversion of configuration, right? So now we have completed the preparation of alkyl halide from alcohol. And from alcohol, these three methods are very important for your examination. From HCl, using HCl, using PCl3, PCl5 or PX3, PX5, and then SOCl2. So after these preparations of alkyl halide from alcohol, now let's move on to the next preparation, that is from alkanes. I hope that this reaction you must have seen in your hydrocarbons chapter, because in hydrocarbon you talk about alkanes, and in the chemical properties of alkane, this is one of the most important reaction whose mechanism is also very, very important, right? So using the free radical halogenation of alkane, we can easily prepare alkyl halide, right? Especially alkyl chloride and alkyl bromide. But again, this reaction is extremely important for our examination. So we need to see this in detail, right? First thing is, what is this reaction? What are the substrate? What are the reagents in this? So substrates and reagents are very simple here. Like if I consider the first alkane, which is methane, right? So I took methane and I reacted it with chlorine. Or in general, let's talk about not chlorine only, in general with halogen in the presence of sunlight or heat, right? So what happens in this reaction? This halogen will remove one of the hydrogen from this sp3 carbon, because sp3 carbon is always preferred for radical substitution for halogen, right? So this halogen will remove one of the hydrogen from this sp3 carbon and 3 hydrogen will be left here, and instead of 1 hydrogen, now you will have a halogen and the byproduct will be HX. So you are getting simply an alkyl halide, right? So this is the generalized reaction of free radical halogenation of alkane. Now, if you talk about its mechanism, so its mechanism we give commonly in 3 steps, right? One is called initiation, one is called propagation, one is called termination, right? In the initiation step, what happens? In this initiation step, what will happen? This halogen, right, in the presence of light or heat, it will decompose, right, homolytically, right? You will be having homolytic fission here. Homolytic fission means out of the bond pair, 1 electron will go on this halogen and 1 electron will go on this halogen. So from this you will be getting halogen radicals, right? Now these halogen radicals, students, try to understand, this needs now one electron because now it is unstable. So what it will do, it will go and it will attack on your substrate, which we call as propagation step, right? In the propagation step, what will happen? The alkane you have, right? Here this CH bond, again it will have homolytic fission, and the halogen will take the hydrogen radical to stabilize, to complete its octet. So this X radical will combine with your hydrogen radical to give a stable HX molecule, and with that you will be getting a carbon radical. So in this reaction, in free radical halogenation of alkane, the first point is that the intermediate are free radical carbon. The intermediates here are free radical of carbon, right? And those free radicals we are getting in the propagation step. Now finally, the third step we have is called as termination step. And in termination step, what can happen, right? In termination, multiple possibilities are there, multiple reactions can happen. This C radical combine with C radical, this C radical can combine with H radical, this C radical can combine with Cl radical, right? But most of the time what will happen, this C radical will combine with a halogen radical to produce your alkyl halide, correct? So most important point here in this reaction is that we are getting a free radical of carbon as intermediate, right? One more thing, this reaction can be repeated again and again, right? You can call monohalogenation, dihalogenation, trihalogenation. Like in our reaction, what I have done, I have reacted this carbon, I have reacted this alkane only once with the halogen. So I am getting monohalo compound, right? So if I am getting monohalo compound, that means I am doing monohalogenation. Sometimes it can be dihalogenation. So one more hydrogen will be replaced by the halogen, trihalogenation. So one more hydrogen will be removed by the halogen. But suppose students, in your examination, if they have not mentioned that it is monohalogenation or dihalogenation or trihalogenation, so by default, we have to understand that they are talking about monohalogenation, or sometimes according to the question, according to the options, we have to think, right? We have to guess that whether monohalogenation or dihalogenation is happening. But I hope you have understood the mechanism, the concept of this reaction, that what is happening here. X2 is breaking into X radical and it is replacing the CH bond, right? And we are getting this alkyl halide. Now, we have certain problems in this reaction which we need to discuss, because from that also we get questions in the examination. The very first problem is we never perform this free radical fluorination. Why? Because free radical fluorination is explosive in nature, right? Also, we never prefer iodination. I'm not saying that we can't do iodination, we can do iodination, but we don't prefer iodination because iodination reaction or free radical iodination of alkane is reversible in nature. Reversible means what? Suppose if you do reaction of methane with iodine in presence of light or heat, right? So you will be getting this, you will be getting iodomethane along with HI. But this reaction, it is reversible in nature. It is reversible in nature. So the efficiency of reaction will be too low. But we have a way by which this reaction can be made to go in forward direction according to the Lee-Chatelier principle. What you can do here in iodination, time to time you can remove this HI. So if you remove HI, if you remove the product, it will drive the reaction in the forward direction. And to remove HI, you can add some oxidizing agents like HiO3 or HNO3. Sometimes they will ask this in the examination, right? So if you oxidize this HI time to time, so this will go in forward direction and then you can perform iodination. But the most comfortable ones are chlorination and bromination. Easily we can perform chlorination and bromination. So in your questions, most of the time you will notice that either the question is based on chlorination or it is based on bromination, right? So this is one of the problem, that fluorination and iodination we don't perform or we don't prefer. Now the next problem is, right, according to number of carbon in your alkane, you get mixture of product. Like if you take methane and you do monohalogenation, right, you get only one alkyl halide. Even if you take ethane and you do monohalogenation, right, you get only one alkyl halide. But when you increase the number of carbon in your alkane, like suppose if I take propane, like CS3, CH2, CS3, and I perform chlorination, for example, for propane. So in this case, there are multiple carbons which are sp3 hybridized, and all of them they have hydrogen. So in your alkane, in your compound, in your substrate, if there is a carbon which is sp3 hybridized and it has CH bond, so there we can have a radical substitution. So in this case, radical substitution is possible on the first carbon, second carbon as well as third carbon. So we will be getting all those products, right? If substitution happens on the first carbon, so from CH3 one hydrogen will be removed and the product will be CH3, CH2, CH2, right, Cl. But suppose if radical halogenation happens on the second carbon, right, so then your product will be CH3, CH, Cl, CH3. And if halogenation here happens on the third carbon, you will be getting the same product, that means 1 chloropropane. So point is, when we have more number of carbon in the alkane, right, then we get more than one product, more than one alkyl halide. Now out of this, one is major, right, and that we have to decide. And for chlorination, bromination, that can be done by comparing the rate of reaction, right? Especially for chlorination, you will have to memorize some of the numbers, right? Those numbers are 1, 3.8 and 5. 1 is used for 1 degree carbon, 3.8 is used for 2 degree carbon, and 5 is used for 3 degree carbon, right? We need these numbers, right, to calculate the major product in case of chlorination. In case of bromination, you can do directly according to the stability of radical, right? In case of bromination, we don't have much issues. In case of bromination, the most stable carbon radical will give you the major product. But in case of chlorination, you will have to memorize these three numbers, 1, 3.8 and 5. And from these numbers, how we get the major product, let me tell you once. So these three are the carbons from which you can obtain your product. These three are the carbons which are sp3 and which has hydrogen. So first of all, assign the degree of carbon. You know degree, how many carbons are attached with a particular carbon. Like here the first carbon is 1 degree. The second carbon is 2 degree because it is attached with 2 carbon, and the third carbon is 1 degree. Now write down what degrees of carbon you have. You have 1 degree, then 2 degree, and this is also 1 degree, and they are giving the same product. So because these two are giving the same product, I will keep them together as 1 degree. Suppose if there are 2 carbons which are 1 degree but they are giving you different products, so then you can name it as 1 degree A, 1 degree B, like that, right? So on 1 degree carbon and 2 degree carbon, just count total number of hydrogen. So on 1 degree carbon, here we have 3 hydrogen, here we have 3 hydrogen, so total 6 hydrogen. On 2 degree carbon, we have 2 hydrogens, right? Now multiply with those numbers into the number of hydrogen, right? So on 1 degree, we have total 6 hydrogen, and for 1 degree, we have to multiply with 1. On 2 degree, we have 2 hydrogens and we have to multiply with 3.8. So this will come out 6, this will come out 7.6. So this is a larger number. So the one for which you are getting the larger number after multiplying these numbers with number of hydrogen will be the major product. So here we are getting 7.6 for the 2 degree carbon. That means this 2 degree carbon will give you the major product. This is your major product here. And of course, this will be minor, right? So in case of chlorination, just memorize these numbers. This is the requirement for you. But when you talk about bromination, so for bromination, it is easy. For bromination, it is easy. In case of bromination, you can directly consider the stability of radical, right? Suppose I have this CS3, CH, CS3, CS3, and I am doing a free radical bromination of this compound. So in this case, if you notice, these are 1 degree carbons and this is a 3 degree carbon. And we know that 3 degree carbon can give you the most stable radical. I hope from your GOC, from your basic organic, you people know very well that 3 degree radicals are more stable than 2 degree, than 1 degree. So in case of bromination, first 3 degree carbon will give you the major. If there is no 3 degree carbon, then 2 degree carbon will give you the major, and then of course 1 degree. So in this case, the major product will be CS3C, CS3, CS3, Br. Of course, you will be getting minor product, which will be CS3CH, CH2, Br, CS3. But this is your major product. So in case of bromination, you don't have to deal with any kind of number. Just use the concept that most stable radical will give you the major product. And from this, students, we get question in the examination. And sometimes in examination here, they will connect this reaction with stereochemistry, especially the optical isomerism part, especially the chiral carbon point. Sometimes they ask questions like this, that we did some free radical chlorination, bromination, then out of the products, how many has chiral carbon, right? How many can show optical isomerism, or total how many isomers we can get. So total isomers, if you have to count, you will have to count the structural as well as optical isomers, right? So we get questions connected to optical activity, optical isomerism from this free radical halogenation. Now one more point, I hope till now you have understood one thing, that if I talk about the reactivity in this case, if I compare, so according to the substrate, you must have understood that 3 degree alkyl halide, not 3 degree alkyl halide, of course, 3 degree carbon will be most reactive towards radical substitution, then 2 degree, then 1 degree for both chlorination and bromination. So according to substrate, you can use this concept, right? That 3 degree carbon is more reactive towards radical halogenation, then 2 degree, then 1 degree, right? In any alkane. And if you compare the reactivity on the basis of your reagent, that means fluorine, chlorine, bromine and iodine. So out of these two, the most reactive one is F2, then Cl2, then Br2, then I2. And here we have a point known as selectivity, if you know, right? The one which is most reactive becomes least selective, right? And the one which is least reactive becomes more selective, right? So reactivity order is highest for F2, then Cl2, then Br2, then I2. But if anyone asks that what is the selectivity order, right? Which can choose the 3 degree, 2 degree, 1 degree carbon out of all these halogens, right? Selectivity. So selectivity is highest for I2, then Br2, then Cl2, then F2. So sometimes you get questions from this according to the reactivity of alkanes, according to degree of carbon, and sometimes according to the reagent, that is fluorine, chlorine, bromine and iodine. So at least this much concept you should know in the free radical halogenation of alkane. But let me remind you that this free radical halogenation of alkane, here we are talking because it is one of the preparation method of alkyl halide, but the same reaction, the same detailed concepts you have to also study in the hydrocarbons chapter, right? So now let's talk about the next preparation. Till now we have seen preparation from alcohol and preparation from alkane. Now let's talk about how we can prepare alkyl halide from alkenes. Again, this reaction you must have seen in your hydrocarbons in the topic alkene, right? And it is one of the addition reaction. Right? The previous one was again substitution, radical substitution, but this one is addition reaction. What happens to students if you take an unsymmetrical alkene? Unsymmetrical alkene means both the carbons, they have different number of hydrogen. One has 2, one has 1. and you treat that with some halo acid, HCl, HBr, HI, right? So here on alkene, the pi bond will break, right? And pi bonds, they are present between the first and second carbon here. So on the first and second carbon, right, one by one, these hydrogens and halogens will be added. So the final product in this case will be CH3, CH, X, CH2H, right? But I hope you must have heard about Markovnikov rule, right? Markovnikov rule is used in these reactions only. That is electrophilic addition reaction of alkene. It is one of the example of electrophilic addition reaction of your alkene. And what Markovnikov rule says? Markovnikov rule says that out of your reagent, electrophiles will be added on that carbon which has more hydrogen, and nucleophile will be added on that carbon which has less hydrogen. Right? So that is Markovnikov rule. You should know Markovnikov rule. And one more point, Markovnikov rule is valid only when your alkene is unsymmetrical. If you have a symmetrical alkene, in that case Markovnikov rule is not valid. But anyway, right, you should know Markovnikov rule very well, but anyway, when you try to decide the product, please follow the mechanism, because mechanism is very easy, and once you understand the mechanism, any reaction you can do between alkene and halo acid. And the reaction is very simple here. If I talk about the mechanism, so its mechanism is something like this. Again, same concept. Don't directly jump into the substrate. First you look at your reagent. Your reagent is HX. We have already seen HX, right, during the reaction of alcohol HX. That HX will ionize easily into H plus and X minus, out of which H plus is electrophile, X minus is nucleophile. Now, if you focus on your substrate, students, which is a alkene, so you should know the property of alkene, right? Try to feel organic chemistry. Feel it. Feel like this. Alcohol is an electron donor species. Similarly, alkene, it also behaves like an electron donating species because it has a pi bond. Alcohol was an electron donating species because it had lone pairs on the oxygen atom. Now, alkene also behaves like an electron donating species because it has pi bond, pi electrons. So, alkenes have always a tendency again to donate electrons to the electrophiles. Now, in this case, when I supply HX to this alkene, what will happen? This alkene will try to share this pi bond with your H plus. But, please notice here, pi bond is shared between 1 and 2 carbon. And in this pi bond, we have only 2 electrons. So, only one bond can be formed. Only one bond can be created. Right? So this H plus here, it can be either attached with the first carbon or with the second carbon. So let's do both. One by one, let's attach this H plus with first carbon and then once by the second carbon. So point is, when you attach H plus with the first carbon, what will happen? CH3, CH, CH2, right? Your hydrogen will attach here with the help of pi bond, and when this pi bond will move towards hydrogen like this, so this carbon is losing electron, the second carbon is losing electron, so it will gain some positive charge, right? Carbocation. So again, point is, during the electrophilic addition reaction of alkene with HX, the intermediate is carbocation. One more possibility is there. Suppose that if your H plus is getting attached with your second carbon, in that case, H will attach here, and on the first carbon, you will get a carbocation. So both are possible, But point is, you know very well that out of these two carbocation, this is 1 degree, this is 2 degree. Or in terms of hyperconjugation, this has 6 hyperconjugates, this has only 2 hyperconjugates. Correct? So of course, the upper one has 6 hyperconjugates, so this is the more stable carbocation. And here, more stable carbocation will be created in more amount, right? So of course, this carbocation, which is more stable, will give you further the major product, right? Means what? After getting this carbocation, now the nucleophile will come, this X minus will come, this will attack here, you will get your major product. But again, please be careful here, because here also in this reaction we are getting carbocation as intermediate. So again, in this case, rearrangements are possible. right? You can have hydride shift, methyl shift, ring expansion. But overall, the addition of HX on alkene can be remembered in two steps. First step, that on your alkene, electrophile will be added in such a way that we get more stable carbocation. We get more stable carbocation. Then if possible, you can do rearrangement to increase the stability of carbocation. And then finally in the second step, the nucleophile will come, it will attack on the carbocation, you will get your product, major product, right? So I hope that for this addition reaction, you have got the mechanism, and if you know the mechanism, students, you don't require that Markovnikov rule, right? You should know Markovnikov rule because sometimes we get a direct question from that Markovnikov rule. But at least while deciding what will be the product, so there you should use the mechanism, right? So now you understood the addition of HX on alkene. Now let's talk about few more points here in this reaction, because certain types of questions we get from this addition reaction of alkene. First point is, students, please notice that when you take alkene with a normal halo acid like HCl, HF, HBr, HI, so it will give you Markovnikov product, right? And the mechanism will be something like in which intermediate is a carbocation. But suppose in this reaction, if you use HBr with some peroxide, this peroxide can be of organic or inorganic, any. Peroxide simply means you should have some OO linkage in your catalyst. So if you use peroxide catalyst, so in that case, right, just remember like this, anti-Markovnikov addition will happen. So if anti-Markovnikov addition will happen, right, so in that case, the bromine, the nucleophile, instead of here, it will be added on the lower degree carbon and hydrogen will be added here, right? And we have only one case, at least in your syllabus, for the addition of alkene with HX. Only one example is there for you where anti-Markovnikov addition happens, and it is HBr with peroxide, right? Suppose if you take peroxide with HCl or water, so in those cases peroxide will have no effect, right? With HCl or water, if you take peroxide, so in those cases you will have normal Markovnikov product. But only in case of HBr peroxide, you will be getting anti-Markovnikov product, and this is also called Kharash effect, right? And if you talk about why it happens, why this happens, so in short, if I tell you the mechanism here, what happens? You have your substrate, right? And you have your reagent, HBr. Now in this, the peroxide, it will decompose into O radical, and this peroxide, it will grab the hydrogen from this HBr. So now because hydrogen has been grabbed by the peroxide, so now you are getting the bromine radical, and this bromine radical is nothing but an electron deficient species. So in this case, instead of hydrogen, instead of H plus, first this bromine radical will attack on your alkene. So this pi bond will be shared by the bromine instead of hydrogen, and that's why you have a reverse addition here. Okay, in this case, again, there is a two possibility. Bromine can attach on the first carbon, on the second carbon, right? But again, you have to follow the same concept. Just like carbocation, here you have to add bromine in such a way that you get more stable radical. So more stable radical we can get if I attach bromine on the first carbon and I get my radical on the second carbon, because here the radical has 5 hyperconjugates. And then later on, this carbon radical will react with HBr to take hydrogen, and again a bromine radical will be produced, which can further react with the second molecule of alkene, and that will proceed. So the major difference, if you notice, between these two addition reaction, the major difference is without peroxide, with HBr, first H plus is getting attached with your alkene. But in the presence of peroxide, what is happening? First, this bromine radical is getting attached, and that's why we are having a reverse product. Here, anti-Markovnikov product. But please always remember that your peroxide will work only with your HBr. It will not work with other reagents like HCl. correct? Few more points are there in this addition reaction. Suppose sometimes if they ask about the reactivity, let me write it here only. If they ask about the reactivity of your substrate, so you know that in this reaction we are getting carbocation as intermediate, right? So the one in which you are getting more stable carbocation will be the more reactive alkene, right? So for substrate we can compare the reactivity on the basis of stability of carbocation, right? Suppose if you have 2, 3, 4 alkenes and for them you have to compare the reactivity. So just add the H plus and see that in which case you are getting more stable carbocation, right? The one in which you are getting more stable carbocation will be the more reactive one, right? And of course if you talk about the reagent, that means halo acid. So just like alcohol, here also the reactivity is Hi, HBr, HCl, then HF, right? Now apart from this reactivity mechanism, Markovnikov, anti-Markovnikov product, one important point I want to tell you, is sometimes, it's very rare, but sometimes you get a question of 1,4 addition. Yeah, 1,4 addition sometimes. Like 1,4 addition, when it will happen, suppose if you have a diene, conjugated diene, like this, CH2, double bond, CH, single bond, CH, double bond, CH2. In this, if you are adding HBr, so in this case, two products are possible. First product, take H plus, add here, you get carbocation here, so Br minus will attach here. So first product can be CH2, double bond, CH, single bond CH, Br and CH3. So this is your normal Markovnikov addition and this is called 1,2 addition. Why? Because hydrogen is added on the first carbon and bromine is added on the second carbon. This is third, this is fourth. Now students, if you notice carefully, in this case, in the very first step, after addition of H plus, the carbocation that we are getting, it is something like this. CH2, double bond, CH, single bond, CH plus CH2 and H. In the first step, after addition of H plus, we are getting this carbocation, and on this carbocation, if bromide will attack, you will get this compound, this product. But suppose, because we have a resonance here, so if resonance happens, then your carbocation will move here on the fourth carbon. And if your carbocation is on fourth carbon, in that case bromide will attack on the fourth carbon. So you will be getting another product here which will look like this, CH2, CH, double bond CH, CH2H and Br. This is called 1,4 addition because hydrogen has been added on the first carbon while the bromide has been added on the fourth carbon. And due to resonance, this pi bond, right, we are shifting in between second and third carbon. So this is 1,2 addition product, this is 1,4 addition product. Both products are possible here, right? Now you will have to decide this according to, especially for you people, according to your syllabus, you have to decide according to the temperature. If low temperature is given, then you get 1,2 product. Temperature, if it is like something 0 degree, minus 80 degree, like that, right? But if temperature is more, high temperature is there, like 30 degrees Celsius, 40 degrees Celsius. So even at normal temperature, you can get what? 1,4 product, 1,4 addition product. And suppose if they have not mentioned the temperature, then by default you have to take normal condition. Normal condition means 25 degrees C at least. So at 25 degrees C, 30 degrees C, you will be getting 1,4 product only, right? So this is a concept you should know, right? Because you don't know that when they will ask these things in the NEET examination. And this is very, very important for you, right? So at normal temperature, high temperature, you get 1,4 product, 1,4 addition product. But at low temperature, 0 degree, minus 10 degree, minus 80 degree, you get 1,2 addition product, right? So now you are done with the addition reaction or electrophilic addition reaction of alkene. But again, this reaction we are discussing here because it is a preparation method for us of the alkyl halide. Now, in the addition only, we have one more preparation method from alkene. But this time, instead of addition of halo acid, you will be having addition of bromine, Br2. And this addition of Br2 to get alkyl halide, we perform in the presence of CCl4. So carbon tetrachloride will be your medium here. Carbon tetrachloride will be your medium here. And it is a very simple addition reaction overall if you notice. Overall if you see, so if you have an alkene, what will happen here? You treat that with Br2 in CCl4 medium. So Br2 will act as electrophile here, right? So because we have two bromine, so one bromine will be added on the first carbon and another bromine will be added on the second carbon. That's it. The product is very easy. The pi bond will break, right? One bromine will be added on the second carbon and another bromine will be added on the first carbon. So product is very simple here. But if you look at this reaction according to stereochemistry, then we have something in this, something important in this. First point is, in this reaction, you won't get a carbocation as intermediate. You won't get a carbocation as intermediate. You will be getting a cyclic intermediate here. Students, in this reaction what happens? Your alkene which is ready to donate electron, your alkene which is ready to donate electron, it will interact with your bromine. Again, alkene has only one task, right, to share its pi bond. So this pi bond will be shared by this bromine, right, and one Br minus will go out. Now point is, normally what happens, the electrophile is added on the first carbon and on the second carbon you get a carbocation. But in this case, instead of carbocation, you will get this type of intermediate. Yeah, a cyclic intermediate, right? And then in the second step, right, we have some partial positive charge here, right? So even though in this reaction we are not getting carbocation intermediate, but the product will be according to Markovnikov. According to Markovnikov, that means the Br minus will attack on this carbon which has less hydrogen. So later on, that Br minus which we were getting from here, it will attack on this bond will be freed, and you will get your dihalide. Of course, this is, if you remember, in the classification we have seen, it is called vicinal dihalide. But one thing you need to notice here, why I said stereochemistry, because these two bromines will be always present opposite of each other. Like students, suppose that if these are your carbons, carbon-carbon double bond. So initially, if first bromine is coming from above the plane, so here it is making the cyclic ring, three-membered ring. Now the next bromine, it will not come from the same side. It will attack from the opposite side, right? So if one bromine is added on these two carbon, right, from above the plane, then the other bromine will be added from below the plane. And that's why the addition of Br2 in presence of CCl4 on alkene, we call it as, it is an example of anti-addition. It is anti-addition. And in this case, of course, rearrangements are not possible because we are not getting a carbocation, right? But anti-addition point is important here because again you get questions related to optical isomerism from this, right? So anti-addition is important. In terms of solid wedge, dashed wedge, if you represent, so if one of the bromine is on solid wedge, then other will be on dashed wedge. That means opposite of each other, right? One modification is there in this reaction, right? Of course, that point is not in the preparation of alkyl halide, but we will have to discuss that. Suppose with Br2, instead of CCl4, if you take water, so in that case, in this step, instead of bromide, H2O will attack, right? And in that case, when you take H2O, on the first carbon you will have bromine, and on the second carbon you will have OH group. You will have OH group because H2O will attack in presence of Br2 and water, right? But for this, for us, it is a preparation method of alkyl halide. Now, after this addition of Br2 on alkene, right, the next preparation we have it is also called as halogen exchange method. It is also called as halogen exchange method, because in this we are not preparing alkyl halide from any other compounds like alkane, alkene or alcohol. From alkyl halide we are preparing alkyl halide. From one halogen, right, by replacing we are getting other halogen compounds. And these two are name reactions, and that's why this is very important for us. One is called Schwarz reaction, right? Like when I was in my 11th, 12th, I used to memorize these two reactions like Schwarz, because its name is small, so it is used for fluorination because fluorine is small, and Finkelstein, right? It has a larger name, so it will be used for the larger halogen, that means iodination. So point is, to prepare alkyl fluoride, we use Schwarz reaction. And at the same time, to prepare alkyl iodide, right, we use our Finkelstein reaction. And these two reactions have completely opposite concepts. Let me tell you why. Students, in Schwarz reaction, what you do, you take some alkyl halide where your halogen can be chlorine or bromine. Your halogen can be chlorine or bromine. And if you have to make alkyl fluoride, so treat this with AgF, right? Or instead of Ag, you can use those metals whose covalent character is high. I hope you remember chemical bonding Fajan's rule. Chemical bonding Fajan's rule. I hope you remember very well. Covalent character and ionic character. So here point is, I am using silver, but instead of silver I can use those metals which have tendency to form covalent bond. Like I can use mercury, right? I can use Sb or any other metal which can form covalent bond, strong covalent bond. Because covalent character and ionic character, it is like a trick for you that covalent and ionic character is the major concept behind your Schwarz and Finkelstein reaction. You know what? What will happen? If you observe carefully, silver prefers covalent bond, right? Silver prefers covalent bond. I have given fluorine to it. Now out of AgF, AgCl, AgBr, if you compare, covalent character is highest for AgBr, then AgCl, then AgF, right? So because that AgF has a low covalent character, so it will try to increase its covalent character. So that's why whether you have a chlorine or bromine here, Ag will combine with that, creating AgX, means AgCl or AgBr, which is more covalent than AgF, right? And along with that, you will be getting alkyl fluoride. So that's the logic of your Schwarz reaction, right? One more thing, because we want this reaction to go in forward direction, we don't want that this reaction should become reversible, right? So to prohibit that, to prohibit the reversibility of this reaction, what we do, we take some polar medium like water in this, right? If you take polar medium, right, in that this AgX, which has high covalent character, it will behave like a precipitate, right? So it will go out of the medium and the reversibility of reaction will be stopped, right? And the concept of Finkelstein reaction, it is exactly opposite. It is based on ionic character. In Finkelstein, what we do, we take alkyl halide, where again halogen can be chlorine or bromine, and we treat that mostly here with NaI. Now here if you notice, sodium is a metal. Sodium is a metal which prefers ionic bond. Silver prefers covalent bond. Sodium prefers ionic bond. And now for sodium halides, if you compare, sodium iodide has the least ionic character. Instead of NaI, NaCl, NaBr both will have more ionic character. So in this case what will happen? NaI will grab this X, that means ClBr, to become more ionic, and then along with that your product will be Ri. And here, to stop the reversibility, because this NaX has more ionic nature, so you take medium such that it should not be ionic. Your medium should not be ionic, right? So here we take those mediums which are not ionic in nature, like acetone, because in acetone this NaX will be not soluble. So it will go out of the medium, acetone medium, and it will not be a reversible reaction then. So for Schwarz-Finkelstein, always study them right together, right? One has a concept of covalent nature, one has a concept of ionic nature, right? In one case you use silver fluoride or mercuric fluoride, mercurous fluoride. In this you use those metals which have ionic nature like sodium, potassium, rubidium. More ionic means much better in case of Finkelstein, right? But point is, overall Finkelstein is a way in which you can prepare alkyl iodide, and Schwarz is a reaction in which you prepare alkyl fluoride, and these two are again easy. They are very easy, but these two are very, very important reactions. One more point I should tell you that both of these reactions, they are example of SN. In the first one, the chloride bromide nucleophiles, they are getting replaced by fluoride nucleophile. In the second one, the chloride bromide nucleophiles, they are getting replaced by the iodide nucleophile. So overall, both Schwarz and Finkelstein reaction, right, if you talk about type of reaction, so they are examples of SN reaction, nucleophilic substitution reaction. So now students, in the preparation of alkyl halide, like we have seen almost all the preparation of alkyl halide, but one more important point, right, that you should know in the preparation of alkyl halide is, like we have a reagent called NBS, right? NBS is known as N-bromosuccinimide, but you should know the function of NBS. Why? Because using NBS, we prepare allyl halides. Using NBS, we prepare allyl halides. But point is, if you talk about the reaction concept or mechanism, so NBS you can remember like this, that it functions, right, in the same way like the bromine and sunlight, right? So the way you decide the major product in case of free radical bromination, same approach you can use, right, in case of NBS. Like point is, if I take suppose this compound CH3 CH double bond CH2, and in this compound, right, if I add NBS, or instead of NBS if I add Br2 sunlight, right? So in both the cases what will happen, these two carbons are sp2 and this is a sp3 carbon, right? So on the sp3 carbon, right, the hydrogen radical will be removed, the carbon radical will be formed, and a bromine will be attached on this sp3 carbon. So using NBS, the product you will be getting here is CH2Br CH double bond CH2, and if you notice, we saw in the classification part that it is called as nothing but allyl bromide, right? In the same way, if I use chlorine sunlight, then also I will be getting allyl chloride, right? So allyl chloride, allyl bromide we can prepare using Cl2 sunlight or Br2 sunlight, but still we have a special reagent NBS, right, whose function is just to prepare allyl bromide. So please keep in mind the function of NBS. And now, after doing all the preparations of haloalkanes, alkyl halides, right? We have not done aryl halide right now. We will do that further. So till now we have completed the preparations of alkyl halide. So after completing preparation of alkyl halide, now let's see some of the questions, like what type of questions we get from these topics in the examination. So you can pause the video if you want. You can do this question by your own first, and then later on you can match the answer, right? So first question here we have is, the given compound is an example of, so a compound is given and we have to see that whether it is a allyl halide, aryl halide, vinyl halide or benzyl halide. So clearly it's a question based on classification. Now if you focus on the structure of this compound, so here you have your halogen, right? And this carbon, which is alpha carbon, if you find hybridization, so it is a sp3 carbon, right? And the very next carbon to it, that means beta carbon, it is sp2 here. Now if you remember, so when it is an open chain or closed chain, right, and when alpha carbon is sp3 and the beta carbon, the next carbon is sp2, so this type of compound we call it as allyl halide, right? So here definitely this is a allylic halide, answer should be B, and definitely the answer is B, that means it is a allyl halide. So just like allyl halide, we saw what is aryl halide, what is alkyl halide, what is vinyl halide, right? And this question we got in the NEET 2023 exam, right? So I told you that we do get questions from the classification also. Now let's move further. Let's see more questions from the preparation of alkyl halide. Can we do this immediately? All of you? I hope you all can do this question, right? Rapidly, because in these type of question you have to just identify that what is your substrate, what is your reagent. Here if you notice, your substrate is an alkene, again unsymmetrical alkene, CH double bond CH2. Reagent is HBr, and we have a catalyst here, peroxide. So if you remember, when HBr is used along with peroxide, so we will be having anti-Markovnikov addition, right? In anti-Markovnikov addition, right, there will be no rearrangements at all, and the bromine, the nucleophile, will be added on this carbon which has more hydrogen, and the hydrogen electrophile will be added on this carbon which has less hydrogen. Now if you see the options carefully, right, so which one? Okay, second one. Just focus carefully. In second option, on this CH2 we have a bromine here, and on this carbon we added hydrogen, so it became CH2, then this CH, then CH3. So it was a question of simple anti-Markovnikov addition, right? Alkene reaction with HBr and peroxide, and we saw that. Even I told you the mechanism also, right? It follows a free radical mechanism. So in this case, the answer should be second. Yes, it is second, and it is a question of anti-Markovnikov addition Kharash effect, and this question, students, we got in the NEET 2021 exam, right? So now let's see the next question again from the preparation of alkyl halide. Can you do this by your own, all of you? The reaction of C6H5 means phenyl ring, CH double bond CH3 with HBr. Now in this case, there is no peroxide, so it will be a normal electrophilic addition according to Markovnikov rule, or according to the, remember, electrophile will be added, more stable carbocation will be formed. So here if I draw my substrate once, so we have a phenyl ring here, then we have CH double bond CH, then CH3. Now according to the mechanism, from HBr first this H plus will add here on the pi bond, right? So H plus can be added on this carbon as well as this carbon, but we need to add H plus in such a way that we get more stable carbocation. So here if you notice, if I add H plus on this carbon and I create carbocation here, so that carbocation will be resonance stabilized by the benzene, right? So that will be the more stable carbocation. So I can clearly decide that here H plus will be added on this carbon, then carbocation will be formed here, and then Br minus will be added here, right? So when pi bond will be removed, H will be added here and Br will be added here. So now check the options, in which case this is the product. C6H5CH2 CHBr, no. C6H5, no, no. Okay, fourth option if you notice clearly, right? In fourth case, the carbon which is attached with benzene ring, on the carbon we have the bromine. And students, if you notice carefully, it is an example of benzyl halide, right? Because on the alpha carbon where your bromine is attached, on the same carbon we have a phenyl ring, right? So in this case I will be getting a benzyl bromide, right? And answer will be the fourth option. Clearly I told you answer will be fourth, and I hope that in these questions you people have got the right answer by your own also, right? These questions now you can do comfortably. And this question, students, we got in AIPMT 2015. So the next question we have is product obtained by chlorination of N-butane. Now if you notice, so this is a question from again free radical halogenation of alkane, but if you look at the options, right, it is related with the optical isomerism topic, right? Point is, when you talk about N-butane, so N-butane is CS3, CH2, CH2, CH3. So we have 4 carbon, they are linearly attached. That means N-butane. Now if you do chlorination, they have not mentioned. So by default, I am assuming that we are doing monochlorination here. So at least you will be getting two products from this, right? Because from this carbon you can have substitution of hydrogen with Cl, and from this carbon also you can have substitution. So you will be getting two products, right? But out of those two, the major one will be CH3, CH2, CH, Cl, CH3. Now students, if I expand this structure a little bit, right, at least where chlorine has been attached, if I expand the major product here, you will notice that in this product we have a chiral carbon, right? I hope you people know very well about chiral carbon, that when a carbon is attached with 4 different atoms or group, like this carbon here, it is attached with methyl, hydrogen, chlorine and ethyl. So as this carbon is attached with 4 different groups, so this carbon is a chiral carbon. And if your product has chiral carbon, that means, right, in the product side, you can have dextro as well as levo. And when both dextro levo are present, right, in equal amount, so we call it racemic mixture. We call it racemic mixture. I hope you know these terms very well, right, that when an optical isomer is there, which can rotate the plane polarized light in clockwise direction, so that is called D form. When the compound rotates plane polarized light, right, in anti-clockwise direction, so that is called L form. And when your compound has some chiral center, has some chiral carbon, but still it is optically inactive, right, so then it is called meso. Now students, a very simple point I have for you. Please remember that if a compound is there which has only one chiral carbon, so it can never be a meso compound. If a compound has only one chiral carbon, so it will be always optically active, and if it is optically active, it will have 2 optical isomers, one is dextro, one is levo, right? In this case, you will be getting mixture of dextro levo, and 50% dextro plus 50% levo mixture is called as racemic mixture. So definitely in this case, the answer will be B. That means we are getting a racemic mixture here. Right? I hope that from your basic organic chemistry, you people know about optical isomerism a little bit. Like what is chiral carbon, what are enantiomers, what are distereomers, what are meso compounds, right? Then how many isomers we can have for a compound containing one chiral carbon or compound containing 2 chiral carbon. For you people in your syllabus, you have to see only 2 types of compound in optical isomerism. Right? Don't go for further. Just see those compounds which have 1 chiral carbon and then those compounds which have 2 chiral carbon. That's it. Not more than 2 chiral carbon you have to discuss according to your syllabus. Now this question we got again in AIPMT 2001. Right? Okay. Can you do the next one by your own? Because this is again from the preparation of alkyl halide from alcohol. You saw these 2 reactions very well, right? That when alcohol is treated with PCl3, right, we get RCl and some byproduct. And when alcohol is treated with PCl5, then also we get RCl with some byproduct. Now if you remember, in case of PCl3, the byproduct we were getting, it was H3PO3. So here I can say that A will be H3PO3, right? But in the second case, when I was using PCl5, so along with HCl, the other byproduct was POCl3. So here A will be H3PO3 and B will be POCl3. If you look at the options, right, so in your second option, it is given that A is H3PO3 and B is POCl3. So of course in this case, the answer will be second one. So sometimes we do get questions, right, from the byproduct also. And if you remember, in case of Darjan's process, the byproducts were SO2 and HCl, both were gases, right? So in this case, of course, your answer is 2. That means we are getting H3PO3 and POCl3 in case of reaction of alcohol with PCl3 and PCl5 respectively, correct? Now, after preparation of alkyl halide, we have to quickly see some of the physical properties of alkyl halide, because sometimes you do get questions from the physical properties also, right? Like first point is, most of the time the alkyl halides are colorless, but sometimes the alkyl bromide and alkyl iodide, right, when they are exposed in air, so they do get color because of the iodine and bromine, right? Many of the alkyl halides, they are sweet smelling in nature, and if you talk about the physical state, so methyl chloride or methyl bromide, right, even your ethyl chloride, they are in gaseous state, but the higher members are in liquid or solid state, right? And finally, this is the point from which you do get questions in the examination. That means compare of boiling point, comparison of boiling point. So comparison of boiling point in your organic chemistry, it's a general concept, right? Some of the points are common, which is everywhere, right? Like in any homologous series, normally you will notice that as the number of carbon increases, right? So boiling point, melting point increases, especially boiling point increases, right? And as your branching will increase, so with branching, because surface area decreases, intermolecular force decreases, that's why with branching your boiling point will decrease, right? Now here, in case of alkyl halide, for the same alkyl group, if you compare alkyl iodide, bromide, chloride, fluoride, so boiling point will be obviously higher for alkyl iodide because it will have larger size, more surface area, more van der Waals force, and it will be lowest for alkyl fluoride. And again, boiling point, if you compare according to branching, so as branching increases, your boiling point will decrease, right? In first case, all atoms are linearly attached. In second case, we have one branch, right? In third case, we have two branches. So as your branching will increase, the boiling point, you will notice that it will gradually decrease. So for boiling point, right, always remember in general that with carbon, boiling point will increase. With number of carbon, boiling point will increase, and with branching, your boiling point will decrease, correct? Now, few more points are there, like if you talk about the density, right? So density will increase with the size of halogen, means as compared to alkyl fluoride, chlorides will have more density, right? Then compared to chloride, bromide will have more density, and as compared to bromide, iodides will have more density. And according to number of halogen also, like suppose if you talk about a compound having one chlorine, right? With a similar mass, if you have another compound which have two chlorine, right, then 3 chlorine, then 4 chlorine. So as the number of halogen atoms will increase, so with that also, because mass increases, that's why the density will also increase. And a very, very noteworthy point here we have, right, regarding dipole moment. Mostly in rest of the organic chapter, you will not discuss about dipole moment, but in this chapter, dipole moment is important, right, especially for the carbon-chlorine bond. Because in general, what you notice that dipole moment depends on the difference in electronegativity. But that's not the fact, right? If you know dipole moment, which is basically the partial charge into distance between two atoms. So dipole moment depends on two factors. One is difference in electronegativity, and the other factor is bond length, right? Now, in this case, we have an exceptional dipole moment if you see trend wise for the carbon-chlorine bond, right? Instead of carbon fluorine, fluorine is more electronegative. So we expect that because carbon fluorine has more electronegativity difference. So generally we think that carbon fluorine bond will have more dipole moment, but that's not true. Instead of carbon fluorine bond, right, the carbon chlorine bond has more dipole moment. In rest of the cases it is regular, right? After this you will be having the carbon bromine bond, and then you will have the carbon iodine bond. But we have abnormal order here for the dipole moment for alkyl chloride and alkyl fluoride, right? CCl bond has a more dipole moment as compared to the CF bond. Please remember this because sometimes they will ask this in your examination, right? So now, after talking about the physical properties of alkyl halide, now let's go into the chemical properties or chemical reactions of alkyl halide. But see, for any organic compound, when you study the chemical reactions or the chemical properties, first you should focus on what types of reaction this compound can show. Like here we are talking about alkyl halide, right? So before diving into the reactions, right, before going into the reactions in details, first you should know that when it comes to alkyl halides have mainly three types of reaction you can say. One is SN reaction, nucleophilic substitution, one is elimination, beta elimination, and the third one is reaction with metal. So for alkyl halide, right, because at the end you have to memorize everything, right? So for alkyl halide you can memorize like this, that alkyl halide have three types of reaction: SN, elimination, beta elimination, and reactions with metal. And those three reactions now one by one we will be seeing, right? So very first is SN reaction or nucleophilic substitution reaction, right? In the preparation part only I told you that we have different mechanism of SN reaction, like one is SN1, one is SN2, right? But before we talk about SN1, SN2, let us see a general reaction for SN reaction of alkyl halide. Students, suppose if I take alkyl halide. So in your alkyl halide, if you see the polarity carefully, right, the halogen atom, because it is more electronegative, it will have some delta negative charge, and the carbon atom will have delta positive charge. So point is, in your alkyl halide, the halogen part is a nucleophile. Now, whenever this alkyl halide will be treated with a reagent which is a nucleophile, so SN reaction will happen, right? The reagent, the nucleophile, it will replace your halogen, and it will take the position of halogen. So halogen here, it will function as a leaving group. Halogen here, it will function as a leaving group, right? And because this X minus nucleophile is replaced by this new nucleophile, you can say that it is a SN reaction. But now the point is, this overall reaction can happen either in SN1 way or in SN2 way. So these two are the different mechanisms we have. So first thing is, let's understand what is the difference between this SN1 and SN2 mechanism, one by one. See, if the SN reaction happens with SN1 mechanism, please remember that then your mechanism will be of two steps, right? And here SN1 means one is your order. The full form of SN1 is substitution of nucleophile by first order kinetics, and SN2 means substitution of nucleophile by second order kinetics. So SN2 reaction, it happens in a single step, one step. If you have the knowledge of chemical kinetics, then this topic will become very easy for you. You know what, in SN1 the reaction happens in two steps. Now in the very first step, what will happen? Your alkyl halide will decompose, right? In first step, your alkyl halide will decompose, and when it will decompose, the electron pair will be taken by halogen, because halogen is more electronegative. So one side you will get a carbocation, along with that this X minus will go out. So first step is fission of the carbon halogen bond in case of SN1. And now in the second step, what will happen? The carbocation you got, right, this will attach with the new nucleophile to give you the final product. But again, please remember, because in SN1 we are getting carbocation as intermediate, so rearrangements are again possible in this reaction. Hydride shift, methyl shift, ring expansion, everything is possible, right? And one more point, here out of these two steps, the first step is RDS, means it is the rate determining step, right? And if you know from your chemical kinetics, the RDS step gives you the rate law. So for this SN1, if I write down the rate law, so rate of reaction will be rate constant into concentration of the reactant in the RDS step, which is Rx power 1. So from here you can see that order of reaction is 1, correct? But in case of SN2, it's not the case. In case of SN2, the reaction will not happen in two steps. Instead of that, it will happen in a single step with one of the transition state, right? If the same reaction, SN reaction happens with SN2 mechanism, in that case what will happen? You will have your alkyl halide, you will have your nucleophile. Now main difference is here this Rx bond will not break. Instead of that, this nucleophile will directly attack on the alpha carbon, right? And for some time, for a very small fraction of time, right, the halogen and the new nucleophile both will be attached, right? But ultimately, because it is unstable, so your halogen will have to leave, right? Because it is a better leaving group as compared to this upcoming nucleophile. So when your halogen will leave, you will get your product, and halogen will go out in form of halide. So this reaction happens in a single step without formation of carbocation. These things you have to focus. And because this is happening in single step, so it is an elementary reaction. And for here, if you write down the rate law, so rate will be rate constant into concentration of Rx power 1, concentration of nucleophile power 1. So that's why here the order is 2, 1 plus 1, and this is called SN2 mechanism. So I hope that you have understood the basic difference between the mechanism of SN1 and SN2. SN1 happens in 2 steps, SN2 happen in 1 step. In case of SN1, the intermediate is carbocation. In case of SN2, there is a no intermediate, right? But apart from this fundamental difference between the mechanism, here some of the points are there from which you will be getting questions in the examination, especially the condition part, students, especially the condition part, right? So first thing is, if you talk about the condition, so in case of SN1, right, in case of SN1, 3 degree and 2 degree alkyl halides will favor. So if your alkyl halide is 3 degree or 2 degree, then it will favor what? SN1 mechanism. But if you have 0 degree or 1 degree alkyl halide, so that will favor what? SN2 mechanism, right? Again, if you talk about the nucleophile, so nucleophiles can be strong, can be weak. Weak nucleophile means which will take time to attack, which will be slow when it will be tried to attack on the substrate. And strong nucleophile means which is very fast in order to attack on the substrate, right? Which has a very high electron density, and it will rapidly attack on the substrate. So if you want SN1, so in that case you need to use weak nucleophile, because if you will be using weak nucleophile, then it will give enough time for the fusion of Rx bond. Once the Rx bond has been broken, then the nucleophile can attack because it is slow. And for SN2, you require strong nucleophile. Now, I will give you some of the examples of strong and weak nucleophile with respect to your halogen, right? Most of the anion, not most, all of the anions, right? Like whether it is Cn minus, whether it is NO2 minus, whether it is OR minus, whether it is RMGX, Grignard, right? All these nucleophiles are strong nucleophile with respect to halogen. So they will prefer SN2 mechanism. But when you talk about neutral water or neutral alcohol, these are not anions, these are neutral molecules. So neutral water, neutral alcohol, these are the examples of weak nucleophile with respect to halogen, right? One more very important point is there, which affects the condition, which is the condition for SN1, SN2, is about medium. Students, when it is SN1 reaction, so SN1 is favored by polar protic medium. Polar protic means like alcohol or water. Polar protic means the medium is polar, but it has availability of H plus ion. So polar protic medium will favor SN1 reaction. But on the other side, if you take polar aprotic medium, so polar aprotic medium will favor your SN2 reaction. In case of polar aprotic, right, most of the time the medium will be DMF or DMSO, right, dimethyl formamide, dimethyl sulfoxide, or sometimes acetone, right, because these are polar medium but they are aprotic, they don't have H plus ion available in the medium. But if you talk about water or alcohol as a medium, so they are polar protic medium. So these are some of the conditions which will decide SN1 and SN2, and you people also will have to decide that whether it is SN1, SN2 according to this. You have to see the degree of alkyl halide, you have to see the strength of nucleophile in the reaction, right? Now, most of the time here from SN1, SN2 in your examination, you will be getting questions regarding reactivity. reactivity of the alkyl halide. So point is very simple. You saw that in case of SN1 reaction, we get carbocation as intermediate. So here, reactivity is decided on the basis of stability of carbocation. In case of SN1, reactivity is decided on the basis of stability of carbocation, right? So point is, from your alkyl halide, if you can get more stable carbocation, that means your alkyl halide will be more reactive towards SN1, right? But in case of SN2, we do not get any carbocation, we do not get any intermediate. So in case of SN2, if you notice, the nucleophile has to directly attack on the alpha carbon. So in that case, the matter will be steric hindrance, right? Point is very simple. In case of SN2, if your alpha carbon is more hindered, right, more groups are attached with your alpha carbon, then the upcoming nucleophile will have difficulty in attacking, right? So its reactivity will be low. So in case of SN2, you can say that our deciding factor will be steric hindrance. Steric hindrance. Less the steric hindrance, more will be the reactivity of alkyl halides towards SN2. Right? If hindrance is more, then your reactivity will be lower. Like if you talk about in terms of degree. So in terms of degree, in case of SN2, most reactive is 1 degree, then 2 degree, then 3 degree. And if you talk about in terms of degree, in case of SN1, right? So because 3 degree carbocation is most stable, then 2 degree, then 1 degree. So that's the order in case of SN1, 3 degree, 2 degree and 1 degree. Right? So now I think you have understood the conditions of SN1, SN2 reaction for alkyl halide. And one more thing, in case of alkyl halide, most of the time you will be having SN2 reaction. Please remember that. You will have SN1 only in two cases, when your nucleophile is water or alcohol, or when you see polar protic medium, right? So now, point is, I have summarized the comparison between SN1 and SN2. If you want, you can pause, you can note it down, right, for your better notes, of course. So we have seen all these points, right? In case of SN1, if you talk about your substrate, right? So I told you 3 degree, 2 degree alkyl halide, or if I have benzyl or allyl halide. So benzyl allyl halide can also produce a stable carbocation. So 3 degree, 2 degree benzyl allyl halides, they will prefer SN1 reaction, while methyl 1 degree, 2 degree, they will prefer what? SN2 reaction, right? Here we have written 2 degree, but 2 degree, in case of 2 degree, you can look at your nucleophile, right? With 2 degree, if you are using weak nucleophile, with 2 degree, if you are using weak nucleophile, then it will be SN1. But with 2 degree, if you are using strong nucleophile, then it will be SN2. So like this you can decide, right? Do not get confused that why 2 degree is written in both the cases. Because degree is not only the criteria, you have to see the rest of the criteria also, strength of nucleophile and medium, right? So with 2 degree strong nucleophile SN2, with 2 degree weak nucleophile SN1. I told you that polar protic medium favors SN1 and polar aprotic favors SN2. I told you the rate laws, right? This is first order, this is second order, right? One very important and interesting point which is related with your stereochemistry is when it is a SN1 reaction. So in case of SN1, because you have carbocation intermediate, right? In case of carbocation, the upcoming nucleophile, because carbocation has a trigonal planar geometry. From your chemical bonding, if you notice, the carbocation has trigonal planar geometry. So for this, the above and below, both sides are empty. So here, the upcoming nucleophile can attack from both the side, right? So in this case, both retention inversion is possible, which we call racemization. When both retention inversion happens, that we call racemization. But please remember that in case of SN1, racemization will occur, right? Both retention inversion will occur, but always inversion will be more than retention. Because initially this carbon will be tetrahedral, right? And the time during which it will convert from tetrahedral to trigonal planar shape, during that time also some reaction will happen. And during that time, whatever reaction will be happening, so in that case only inversion will happen. So always in SN1, the acimization will happen, but inversion will be more, percentage of inversion will be more as compared to retention. But in case of SN2, there is no retention, right? In case of SN2, there will be always inversion because it has a backside attack, right? And finally, if you talk about rearrangements, of course, in case of SN1, the intermediate is carbocation. So in this case, rearrangement is possible. And in case of SN2, there will be no rearrangement because we don't have any carbocation formation in case of SN2, right? So with this, you can clearly identify that when SN1 is happening, when SN2 is happening. Now, in the SN reaction part, one more point is there, right? Regarding your ambidentate nucleophile. Students, I hope that you must have heard about ambidentate nucleophile, right? Those nucleophiles which have more than one attacking site. Some of them are very famous for you, like cyanide, right? Nitro and thiocyanide. These are some of the ambidentate nucleophiles we have. Now, in case of ambidentate nucleophiles, you will have to focus on what reagent you are using. And here again, right, you will have to focus on when you have covalent bond, when you have ionic bond. Like, let me tell you something. For cyanide, if you take AgCN, so AgCN has this structure, right? And for the same cyanide, if you take NaCN, so NaCN has this structure. Now, when you will be using AgCN, so because carbon silver has covalent bond, carbon has no free electron pair. So in this case, electron pair is available only at nitrogen. So in this case, nitrogen will attack, and after the reaction with alkyl halide, you will be getting isocyanide. But when you are using NaCN, so in this case, you notice that carbon, nitrogen both has electron pair, but carbon has a negative charge, nitrogen is neutral. So the atom with negative charge will be a better nucleophile, will be a stronger nucleophile because it has negative charge. So out of carbon, nitrogen in case of NaCN, because C has negative charge, now here C will attack on your alpha carbon. And in this case, the product will be alkyl cyanide. So with AgCN, you will be getting isocyanide. With NaCN, you will be getting simple cyanide. Same concept you can apply for the rest. Like if you talk about NO2 minus. So when you take AgNO2, AgNO2 has this structure. Now in this case, if you notice, in AgNO2, oxygen Ag has a covalent bond, right? Because silver creates covalent bond. Now nitrogen, oxygen both have lone pair. Both are neutral, right? None of them has negative charge. So here, if I check the electropositive character, so nitrogen is more electropositive. Nitrogen is less electronegative. So here nitrogen will have more tendency to donate electron. So in this case, you will be getting, right, attacked by nitrogen. But here, if you take NaNO2, so in case of NaNO2, now the scenario will be completely different. Now you have lone pairs on both oxygen, nitrogen, right? But oxygen has negative charge. So the atom having negative charge is a better nucleophile. So in this case now, nitrogen will not attack. Instead of that, oxygen will attack, right? So that's how the ambidentate nucleophile, right? It depends on what reagent you are using, whether it is AgNO2, KNO2, NaNO2, or AgCN, KCN, or NaCN, right? So this is a small concept of ambidentate nucleophile which you should know, and you should not memorize these things, right? I hope you know that if I know the structure, I can decide, right? And for the nucleophilic character, first point is charge. The atom which has negative charge will be a better nucleophile, right? If both the atoms are neutral or both have negative charge, then you decide with electropositive character. The atom which is more electropositive will be a better nucleophile for you, right? So after the SN reaction of alkyl halide, the next reaction we have, right, which is again important, is elimination. And this reaction has so many names, right? It is also called as beta elimination reaction, beta elimination reaction, or it is also called as dehydrohalogenation reaction, dehydrohalogenation reaction. So first let's understand the concept of this reaction. What is the meaning of beta elimination or dehydrohalogenation? Students, if you take an alkyl halide, the reaction is very simple. Elimination, very simple. If you take an alkyl halide, right, in which the beta carbon, of course this is your alpha carbon where your halogen is attached. If your beta carbon has hydrogen atom on it, right, and you add base, base like it can be alcoholic KOH, or sometimes it can be alkoxide, So if you add a base like alcoholic KOH or sodium alkoxide, so what base will do here? It will eliminate halogen from the alpha carbon and hydrogen from the beta carbon. And because hydrogen is getting removed from the beta carbon, that's why the name of the reaction is beta elimination. Now point is, when halogen is removed from alpha carbon, this bond pair will go with halogen, and this bond pair will remain with carbon, and it will move towards your alpha carbon. So ultimately the product of this reaction is alkene. This reaction you have seen already in your hydrocarbons chapter also, because of course it's a property of alkyl halide, but this reaction is also used for the preparation of alkenes, But I hope you have understood one thing, that whenever you see that there is an alkyl halide and we are adding some base to it, so it can have what? Elimination reaction. Now one point I would like to clear here only, because sometimes you will be having a doubt between what? SN and elimination reaction. So here if you are using alcoholic KOH, so in that case definitely elimination will happen. But if you are using alkoxide, so please focus, if your alkyl halide is 1 degree, and with that if you are using alkoxide, right, so in that case elimination will not happen. With 1 degree you will be having SN2 reaction, right? But instead of 1 degree, if I am using 2 degree or 3 degree alkyl halide with alkoxide, so in that case I will be having elimination. And always remember that heat or high temperature is a perfect criteria for elimination, right? Heat supports elimination. But this point you need to always remember. In case of alcoholic KOH, no doubt it will be having elimination only. But if you have alkoxide, right? So in case of alkoxide, if your alkyl halide is 1 degree, then you will not have elimination, you will have SN2 reaction, right? And with 2 degree, 3 degree, both will happen, but elimination will dominate. Right? Now, point is this, just like your SN reaction, elimination also happens in 3 ways, E1, E2 and E1CV. Correct? E1 is quite, I can't say similar because both are completely different reaction. One is substitution, one is elimination. But in terms of carbocation formation, E1 is similar, right? E1 happens in 2 steps, E2 happens in single step, but again E1CB happens in 2 steps, right? The main difference is, see, during elimination both hydrogen, halogen will be removed. But first which atom is getting removed, right? That decides your mechanism. During the elimination, suppose if your halogen is getting removed first. So first if halogen will be removed, then you will get a carbocation intermediate, right? So when first halogen is getting removed, right, and you get a carbocation, so that mechanism will be E1, right? Further, the next step is very simple. Once you got carbocation, then hyperconjugation will happen, or here again rearrangement is possible because we are getting carbocation. But ultimately with the most stable carbocation, finally you will have hyperconjugation, you will get your alkene. But point is, instead of halogen, if hydrogen is getting removed first, so then it will be E1CB mechanism. And when hydrogen is getting removed first, so in that case this bond pair will move on carbon, you will get a carboanion intermediate.
So by the removal of hydrogen, if you are getting a carboanion intermediate, so that is even CB mechanism. And here again in the next step, it is very easy. In the next step, this lone pair will go here and your halogen will go out, right? In case of E2, both are removed simultaneously. Both are removed simultaneously. On one side, the H will be removed. On one side, the X will be removed. So in case of E2, you won't have any intermediate. You will directly be having the product, right? So in this case, there is no intermediate. There is no intermediate, right? And just like SN1, we can compare the conditions of E1, E2 and E1 CB, right? And they are quite similar, like E1 is favored by 3 degree alkyl halide, E2 is favored by 1 degree and 2 degree alkyl halide. E1 CB is a completely different case, right? E1 CB will happen only when you are getting some stable carboanion. So point is, in case of alkyl halide, mostly you will have E1 or E2 mechanism. 3 degree E1, 1 degree, 2 degree E2. But again, apart from degree, there are other factors, right? Like if you talk about base, strength of base, strength of base. So strong base will favor E2 and weak base will favor E1. Strong base will favor E2 and weak base will favor E1. This much point if you know, then believe me, you will be able to do all the questions. You will be able to solve all the questions, right? But apart from mechanism, apart from these points, we have another point here. Suppose students, sometimes if your alkyl halide has more than one beta carbon, then you will be getting more than one products, but out of that one will be major. Like suppose if I have this reaction, CH3, CH2, CH, Br, CH3 with alcoholic KOH, with alcoholic KOH. So in this case, of course, elimination will happen, right? From alpha carbon, halogen will go out. But here if you notice, this is a beta carbon adjacent, beta 1. This is another beta carbon, let's say beta 2. And from beta 1, beta 2, you will be getting different products, right? From beta 1, if hydrogen is getting out, so your product will be CH3, CH2, CH, double bond, CH2. And from beta 2, if hydrogen is going out, then your product will be CH3, CH, double bond, CH, CH3. So both product will be formed, but out of these two, the second one will be the major product. The second one will be the major product according to Zaitsev rule. Okay, sometimes Zaitzev's spelling is Zaitsevs. So do not get confused by that. Do not go into the spelling part. So the major in this elimination we decide according to Zaitsev rule. Now what Zaitsev rule says? It says that more stable alkene will be the major product. Stability of alkene is decided by hyperconjugation. Like in the first alkene, if you notice for this CC double bond, this is your sp3 carbon from where hyperconjugation can happen, and it has only 2 alpha hydrogen, only 2 hyperconjugations are possible. In the second case, if you notice, for this CC double bond, this is sp3 carbon, this is sp3 carbon, here you have 3 hydrogen, here you have 3 hydrogen, total 6 hyperconjugates are possible. So more the hyperconjugates of an alkene we have, more is the stability. And what Zaitsev rule suggests? It suggests that more stable alkene will be the major product, right? And most of the time during the elimination of alkyl halide, your product will be Zaitsev product. Most of the time, not always. Please remember, there are two cases, right? When you are having elimination of alkyl fluoride and when you are using bulky base. In your syllabus bulky base, we have just one example, tert butoxide, this one, tert butoxide, right? So when you are having elimination of alkyl fluoride or when you are using bulky base, so in these two cases, right, you will be having anti-Zaitsev product, right? So just these two cases, alkyl fluoride and bulky base, you will have what? anti-ZZ product. In rest of the cases, you will be having ZZ product. So here point is, suppose instead of bromine, if I have fluorine here, so in that case, this will be the major product. Instead of alcoholic KOH, if I use this base, irrespective of what halogen I have, chlorine, bromine, if I use bulky base, then this will be the major product. But apart from alkyl fluoride and bulky base, in rest of the cases, you will be having ZZ product as the major product. So now I think in beta elimination, you can easily decide which one will be major, which will be minor, right? So this is your elimination reaction of alkyl halide. Now finally, the third reaction, right, of alkyl halide is reaction with metal, where you have to see two reactions. In metals, we have two reactions. One is with sodium metal and one is with magnesium metal, right? So first let's talk about with sodium metal. I hope you people know this reaction very well, because when alkyl halide reacts with sodium metal in dry ether medium, so it produces alkane, and it is one of the name reactions we have. It is called Wurtz reaction. In this reaction, what happens? In general, you take alkyl halide, you have sodium. So remember like this, sodium has an electron in the valence shell. This electron it will provide to halogen. So halogen will go out by homolytic fission. The byproduct will be NaX, right? And now you have R radical. R radical is the intermediate in this reaction. So if two RX are there, two alkyl halides are there, so you will be getting two radicals. So those two radicals will eventually combine to give you RR. Of course, two sodium will be there, two NaX will be formed. So it is a method of preparation of alkane as well, right? But again, in Wurtz reaction, you can notice that from one alkyl halide, a kind of dimerization is happening, right? So we can't get methane from this reaction. From Wurtz reaction, you can't prepare methane. Also, we do not prefer preparation of alkane having odd number of carbon from this method, because for that you will have to use a mixture of alkyl halide, right? And in that case, you will be getting multiple alkanes. Right? But point is, one more point is there. Suppose that if a compound is there like this, in which a single compound has two halogens. Now here if you add sodium, so again same thing will happen. Sodium will give electron to this bromine and this bromine. Now in one structure only, here two radicals will be created. So if two radicals are getting created in the single compound, right, so themselves they will attach with each other. In that case, your product will be something like this, a kind of bicyclo compounds, right? So in Wurtz reaction, just remember one point, that sodium will provide electron to halogen, right? X will go out, halogen will go out, a radical will be created, and then that radical will be combining with another radical, right? It is possible within the molecule and it is possible between two molecules also, right? And from Wurtz reaction, we never prefer preparation of alkane having odd number of carbon, right? Now, after this Wurtz reaction, after reaction with sodium metal, one more but a very important reaction of alkyl halide we have, that is reaction with magnesium metal. Why? Because when alkyl halide reacts with magnesium metal, it produces Grignard reagent. Which is a very, very important compound for the whole organic chemistry. What happens when you take alkyl halide and you treat that with magnesium, right? So it gives you RMgX. And if you talk about the concept of this reaction, so you can remember like this. You have Rx, right? Magnesium have two electrons, right? So if it provides two electrons to halogen, this will decompose and electron pairs will go on to alkyl group. So you will be having a R minus, and this side you will be having Mgx, while your Mg will have a plus charge. Later on, this R minus Mg plus will combine to give you RMgX. But always remember the ionic nature of Grignard reagent, right? In Grignard reagent, you have two parts. One part is R minus carboanion, one part is Mg plus. Why I am saying this? Because later on, whenever you are going to do reactions of Grignard reagent, right? So during the reaction of Grignard reagent, just consider that Grignard reagent is nothing but a carboanion plus MgX plus part. It means the Grignard reagent has a nucleophilic part R minus, right, and an electrophilic part MgX plus. It will help you during the reactions of Grignard reagent. But point is, Rx with sodium is called Wood's reaction, while Rx with magnesium will give you Grignard reagent. Now students, let's see some of the questions from the properties of alkyl halide that we have seen, right? And anytime you can pause the video, you can do the question by your own, and later on you can match the answers, right? So the first question we have is the major product of the following reaction. The major product of the following reaction. And if you notice, in the substrate side you have benzene ring, ketone group, cyanide group, and we are treating this with Grignard reagent. Now, just now I have told you that whenever you see Grignard reagent in your reaction, think like this, that Grignard is nothing but CS3 minus Mg plus ions, right? Just like this. You have a carboanion and you have a Mg plus cation. And this carboanion in your substrate, it will be added on positive center where you have delta positive charge, and this Mg plus will be added on that atom which has negative charge, because negative positive they attracts. Now, if you notice overall the polarity. So let me redraw it once. You have a benzene ring, then you have a ketonic group, then you have two more carbon in between, and then you have cyanide group. So if you check the polarity, so in your carbonyl group, in the ketone group, students, this carbon atom will have delta positive charge and this oxygen atom will have delta negative charge, right? And for the cyanide part, again, this carbon has delta positive, this nitrogen has delta negative. So please focus here step by step, like it is written 1 here, 2 here. So first we are treating with Grignard, and then later on we are doing hydrolysis, right? So first when you treat with Grignard in excess, so one of the Grignard molecule, CS3 minus Mg plus Br, it will be added on the ketonic group. How? This C minus will attack on this carbon, pi bond will break, it will go on to oxygen, and then oxygen will attach your MgBr part. And one more Grignard molecule will be attached here on the cyanide part, right? This C minus will attack on this carbon, one of the pi bond will break, and then nitrogen will attach this MgBr. So it's a kind of addition reaction you have. So after this addition of Grignard reagent, the new structure, right, after first step will be something like this. You will have your benzene, then this carbon attached with OMgBr. We have a methyl group here now. In between we have two more carbons, and then we have this cyanide group, which will become C double bond N, MgBr plus minus, and here you have a methyl group. Now point is, in the second step, when you will do hydrolysis, so during your hydrolysis, students, from this O minus Mg plus part, this MgBr part will be removed and oxygen will be protonated. So this will become OH group. And I hope in your aldehyde ketone chapter, right, somewhere you must have seen that when we have this sort of structure C double bond N MgBr, right, so during hydrolysis, this C double bond N bond will break and you will get oxygen there, a ketonic group. So overall in this case, right, after first and then second step, the final product will be on this carbon, you will have a OHCS3, and here you have a ketone group and then CS3. Now if you check the options carefully, so you will notice that in the third option we have the same thing. On this carbon we have OH, CS3, and then we have here ketone. So answer of this question should be third. And yes, third is the answer. And students, this question again we got in the NEET 2025 examination. So it's a very recent question, right? Let's not stop here. Let's do more questions from the properties or reactions of alkyl halide. Can you do it by your own? The concept of this reaction I have told you completely, so you can do this question now by your own if you have followed the session, if you have followed the video, right? So here the major product C in the below mentioned reaction they are asking. So a sequence of reaction is given, and one by one we have to see what will be the product. So if you notice in the very first step, here we have a alkyl halide, right? If I redraw the structure, at least around the alpha beta carbon you should draw complete structure. You should show all the bonds, right? Like this is the beta carbon here, which has 2 hydrogen, CH2. Then this is the alpha carbon here, which has 2 hydrogen and 1 bromine. Now point is, in the very first step we are treating this alkyl bromide or propyl bromide with alcoholic KOH. So now you know very well that alcoholic KOH will do beta elimination. Alcoholic KOH will do beta elimination. So from this alpha and beta carbon, bromine and hydrogen will be removed, right? And the product here will be an alkene. More precisely, I should say propene. CH3CH, double bond CH2. So this is your A. This is your A. Now further, this A has been treated with HBr. So you know that when alkene is treated with HBr without peroxide, so we get a simple electrophilic addition reaction, right? First H plus will be added, then more stable carbocation will be formed, and then later on, after rearrangement, the bromide will attack on the carbocation. So in this case, if you notice, if you treat this A with HBr, what will happen, students? H plus will attach on this carbon. Here you will get carbocation, which is already stable, and no rearrangement is possible. So finally Br minus will attack here. So after treatment of A with HBr, the next product we will be having is CS3, CH, Br, and here it will be 2 hydrogen and 1 more hydrogen, CS3. So this is your B. But we have to not stop here. This B is further treated with aqueous KOH. Now students, let me tell you one thing. Alcoholic KOH will be doing beta elimination, But instead of alcoholic KOH, if I use aqueous KOH, so aqueous KOH will do SN reaction, will do substitution reaction. So basically, if I treat this compound with aqueous KOH, that means now I have OH minus nucleophile. So this OH minus nucleophile will do SN reaction, will substitute this bromine, right? And after this SN reaction, the final product will be CS3, CH, OH and CS3. And I think this is our C. And they are asking that what is the product C. Now if you notice, they have given the name. I hope you all know how to write IUPAC name, correct? For this compound, if I have to write the IUPAC name, so this is my parent chain. Numbering you can do from any side because on second carbon you are getting OH from any side. So 1, 2, 3. For 3 carbon, word root is prop. Single bonds are there between carbon. So primary suffix will be ane and secondary suffix will be 2-ol. So the compound will be propane 2-ol. Propane 2-ol. Answer will be B. And again, this question we got in the NEET 2024 examination. Right? So now you can think that what type of questions we get in the examination. We get questions from the reagents that we discuss in the preparation part or the properties part, right? Now, let's see the next question. We saw that SN reactions are very important, and in the SN reaction part, especially the reactivity, the comparison of reactivity of compounds in SN1 or SN2 is very important. Many times we get question from reactivity in SN1 and SN2, and I have told you how to decide reactivity, right? When it is a SN1 reaction, right? Remove the halogen from your compound, create the carbocation, and the most stable carbocation will be most reactive. And in case of SN2, least hindered, right, alpha carbon will be most reactive. So in this case, we have 4 options and we have to decide which one will undergo fastest SN1 reaction. Now to check that, what you need to do, just take out the halogen. Like in the first option, we have a bromine here. if I remove this bromine and I create a carbocation, so it will be something like this. I hope you know that if a carbocation is there on the benzene ring, it is highly unstable, right? It will never be formed. So first is already eliminated. Now if you check the second one, if you remove this bromine, so in this case the carbocation you will be getting is this CS3 plus. In the third case, your carbocation will be a cyclohexane ring. Okay, we have to remove bromine, so carbocation will be formed here, and in the last case here. Now I hope that you know how to decide stability of carbocation, right? Based on aromaticity, resonance, hyperconjugation, inductive effect. So one by one, if you check, this carbocation is highly unstable, so this will not at all undergo SN1 reaction, right? Now for the rest of three, if you notice, in the second case for this carbocation, we have a resonance effect. We have resonance effect because it is attached with benzene. In the third and fourth case, we do not have resonance. So clearly, the carbocation we are getting from the second option is most stable one. So obviously in this case, the most reactive in SN1 will be second one. But if you compare third, fourth, right? So in third, fourth, if you notice, this carbocation, it does not have resonance, it has hyperconjugation effect, and it has one alpha hydrogen, so it has only one hyperconjugation. And for this one, again we don't have resonance, and for this case, we have 2 and 2, total 4 alpha hydrogen, means we have total 4 hyperconjugates. So clearly, fourth carbocation is more stable than the third one. So if you have to compare the reactivity here, the most reactive one will be second, then fourth, then third, and then first. So that's how you can compare the reactivity towards SN1 just by drawing the carbocation by removing the halogen from the alkyl halide. So of course in this case, in this question, the answer will be second, yeah, and this question again we got in the same NEET 2024 examination, right? So now the next question we have is, again we have a conversion kind of question here from the properties of alkyl halide, but you will notice that some of the further reactions, some of the reactions from the future chapter like amine and acid is included here, right? Because see, in the organic chemistry, most of the time they will frame questions in which you will require knowledge of all the chapters of organic, right? You will require knowledge of haloalkanes also, aldehyde ketone also, amine also, alcohol also. So always see, it's always better to practice questions in the organic chemistry after completing all the chapters. Once you have done all the chapters, amines, aldehyde, ketone, acid, alcohol, phenol, ether, haloalkanes, haloarenes, once you have hydrocarbons also, once you have done all the chapters, then you can practice these types of questions. So here, the question is, in the first part, in the substrate, we have propyl iodide and we are treating that with NaCN. Now if you check polarity, Na plus Cn minus, right? I told you that cyanide is ambidentate nucleophile. When you take NaCN or KCN, so in that case, this carbon will attack, right? And you will be having SN2 reaction here. So after SN2 reaction, you will get CH3, CH2, CH2 and cyanide group, C triple bond N. So this is your A. Now this A is getting partially hydrolyzed, right? Now this point you will see in the carboxylic acid chapter that when cyanide, it is completely hydrolyzed, we get carboxylic acid. But when it is partially hydrolyzed in the presence of base, so this cyanide converts into amide. This cyanide converts into amide. So from here, by partial hydrolysis, we will be getting amide group, C double bond O NH2. So this is your B. This is your B. And this is a very famous reagent, students. With amide, if I add Br2NaOH, with amide, if I add Br2NaOH, it's a name reaction. It is called Hofmann-bromamide degradation. Very famous reaction in the amine chapter. It comes under preparation of amine. So with amide, if you treat Br2NaOH, it will simply remove this carbonyl group and this nitrogen will attach with this carbon. You will be getting propyl amine from this. CS3, CH2, CH2, NH2. So this will be the final product here, that is C. Right? It is nothing but propanamine, or common name will be propylamine. So if you check at the options, it is butanamide, no. Alpha bromobutanoic acid, no. Propylamine, yes, yes. Here the answer will be, of course, C. Answer will be C. Of course, it will be C. You can see that. But I think from this particular question you have understood one thing, that you need knowledge of each and every chapter of organic, right, in order to solve these types of questions. And this question again came in NEET 2024 examination. Now, let's see the next question. Which of the following reaction of alkyl halide produces isonitrile? Isonitrile means NC group as a major product. So some of the reactions are mentioned here. If you check one by one, okay, we know that cyanide is an ambidentate nucleophile, so it depends on structure, right? So in the first option, you have Rx, which is getting treated with HCN. So first of all, for the first reaction, the extent of reaction will be very, very low because HCN is a weak acid. HCN is a weak acid. But anyway, HCN will ionize into H plus and Cn minus. And if you have Cn minus, then this C will attack on this carbon. You will be getting cyanide, not isonitrile. In the second option, I think I have mentioned this point, right? That when you have AgCN, so in AgCN, Ag is attached with carbon with covalent bond. So free electron is present only on the nitrogen. So nitrogen will attack here on this carbon, producing isocyanide. So in the B option, in the B reaction, you will be getting isocyanide. And again, if you check the third, fourth option, so in KCN you have K plus and Cn minus ion. So again, carbon will attack. You will be getting cyanide here. In NaCN, again you have Na plus Cn minus. So again, C will attack, right? So only in the B reaction, you will be getting isocyanide. Right? In the first case, the extent of reaction will be too low, right? But still, in some amounts, you will be getting cyanide. And in third, fourth, you will be getting only cyanide. So here, the correct option should be B only. That means your answer will be C. And of course, it is your answer, C. And again, this question, students, it's a PYQ. We got that in NEET 2023 examination. We got in NEET 2023 examination, this question. I remember each and every question. Like just by looking at the question, I can tell you that which year that particular question came. So that sort of practice you should also have, right? Especially in the organic chemistry. Now, can you do this question completely by your own now, all of you? Identify the correct product in the following reaction. So, again we have a conversion type of problem. We have a cyclobutyl group here and a chlorine functional group here, and we are treating with KCN. So again, KCN is K plus and Cn minus. So in the very first step, you will have SN2 reaction because cyanide is a strong nucleophile, right? And this is 2-degree carbon, right? So it's a SN2, not SN1. So SN2 reaction will happen. The chlorine will be replaced and you will be getting a cyanide group here in the first step. Then in the second step, you are doing hydrolysis in acidic medium with heat. So acidic medium if you use, that means complete hydrolysis. Just now we saw that partial hydrolysis of cyanide gives amide. But complete hydrolysis or hydrolysis in acidic medium for cyanide, it converts into carboxylic acid. So after second step, the cyanide group will convert into carboxylic acid group, right? And then you are treating with Br2 red phosphorus in water. It's a very famous reaction. Again, it's a name reaction. If you remember, it is called HVZ reaction, Hell-Volhard-Zielinski. And this reaction, HVZ reaction, is there in your carboxylic acid chapter. So during that, what happens? what happens when I take Br2 and red phosphorus, the bromine will be substituted on the alpha carbon in this carboxylic acid group, right? So you will have COH group, and on the alpha carbon now hydrogen will be replaced by the bromine, so you will get this type of product. And if you check at the options, in the second option we have this product. So of course in this case answer will be 2, but I hope that you people remember very well HVZ reaction, right? Because in carboxylic acid chapter, if you check out that chapter, so in that, in the name reaction part, HVZ is the most important reaction, correct? Now, of course, in this case, answer will be 2. That means COH and Br. Now, let's see the next question. What's the question? The major product formed in the dehydrohalogenation or beta elimination of 2-bromopentane. So, it's a question from elimination reaction of alkyl halide. You know that from alkyl halides reaction point of view, you will be getting questions only from those 3 parts: SN reaction, elimination reaction, and reaction with metal. So here the substrate is 2-bromopentane. So what is 2-bromopentane, students? CH3, CH, Br, CH2, CH2, CH3. This is 2-bromopentane. 1, 2, 3, 4, 5. Now, okay, they have said that we are getting pen2 in. Of course, we know that. Point is, when elimination will happen, so in this structure, this is your alpha carbon, and you have 2 beta carbons. This is beta 1, this is beta 2. And from both beta, we are getting different products, right? So, in normal cases, if it's not alkyl fluoride, if it's not bulky base, you know that in normal cases, we use Setzeff rule, right? That means a more stable alkene will be the major product to decide major product. And that's what they are asking. This product formation is based on, of course it is based on Setzeff rule. In all generally normal eliminations, right, we use Setzeff rule to decide the major product. So in this case, of course, the answer will be B, that is Setzeff rule. So it's a direct question. Like if you know how to decide major product in elimination, you can do this. And this direct question came in the NEET 2021 examination, students, right? So we get question from SN reaction, we get question from elimination reaction. Now, let's check the next question now. Which of the following alkane cannot be made in good yield by Woods reaction? So again, this is the third part, right? Where we saw reaction of alkyl halide with metal, and when your alkyl halide reacts with sodium metal, so that is called as Woods reaction, correct? So point is, in Woods reaction, I told you we have some problem, like we can't prepare methane, and we do not prefer, right, to prepare alkanes having odd number of carbon. Now one by one if you check, hexane has 6 carbon, which is even. 2,3-dimethyl butane, it's a symmetrical compound. Butane, again it has an even number of carbon. But students, if you check heptane, heptane has 7 carbon, which is odd. So odd carbon containing alkane we never prefer from Woods reaction. So C should be the answer in this. Of course it is C. And let me tell you one thing, this question came in NEET 2020. Why we do not prefer to prepare odd carbon alkanes by Woods reaction? Let me tell you that. Suppose I am going to prepare heptane by Woods reaction. Heptane has 7 carbon. So to prepare that, what I need to do, I need to take one alkyl halide having 3 carbon, and with that I will have to add another alkyl halide having 4 carbon, right? When these two mixtures, they are treated with sodium, right? So from here you will be getting C radical, and from here you will be getting C radical. If these two radicals will combine, you will get heptane. So we can prepare heptane, but the problem is you cannot stop the radicals. There can be self combination. Suppose if this propyl radical combines with another propyl radical, so when 2 propyl radicals will combine along with heptane, you will get hexane also, right? And similarly, if this butyl radical combines with another butyl radical, so then you will be getting octane. So point is, you were trying to prepare heptane, but apart from heptane, you got hexane, octane like a gift, right? So that's the problem. We get mixture of product, and that's why we never support preparation of odd number of carbons alkane by Wood's reaction, right? So this question we got in NEET 2020 from Wood's reaction or reaction of alkyl halide from sodium metal, you can say. Now, can you do this one? I think this is a direct question again. Okay, so it looks that this question is from the condition of SN reaction. Consider the reaction. The reaction will be fastest in, so some medium has been given, ethanol, methanol, DMF, water. And you have to decide that this particular reaction will be fastest in which of the following medium, right? It's very easy. Students, if you have to decide SN1, SN2, first you check the substrate and its degree, right? In this case, the alpha carbon, it is 1 degree. Now we know that 1 degree will favor SN2, not SN1. So here your substrate is favoring what? SN2 reaction. Now check the reagent. You have NaCN, in which cyanide is the nucleophile, and cyanide is much stronger than halide. So you have a strong nucleophile here, and again strong nucleophile favors what? SN2. So point is, if the substrate and reagent both are favoring SN2, so overall this reaction will be SN2, right? Of course, so you will be getting cyanide as a product here, but point is, I told you that SN2 reaction will be faster in polar aprotic medium, while SN1 reaction will be faster in polar protic medium, right? So point is, ethanol, methanol and water, these are polar protic medium. So these will favor SN1 reaction. Here we have SN2, right? So in case of SN2, if I choose DMF, dimethyl formamide, right, or DMSO or acetone, so that will favor SN2. So in this case, the answer should be C, because it is SN2. So SN2 will be faster in polar aprotic medium like DMF, DMSO and acetone. Of course, answer is C. And this question we got in NEET 2016 examination. Now, let's do one more. Again, we have a question from SN reaction itself, but this time it is from stereochemistry. In an SN1 reaction on the chiral center. Okay, let me tell you one thing, right? In this chapter, we need some stereochemistry, and for that stereochemistry, you should be good at optical isomerism part, right? So if you have any problem in the optical isomerism part, right, very soon we are going to release the one shot of isomerism, where I will be talking about structural, geometrical, optical isomerisms, right? So please see that video, right? Because once your optical isomerism part is good, right, you understands everything: chiral carbon, chiral center, optically active compound, optically inactive compound, right? Different terms, enantiomers, diastereomers, mesomers. So that will help you in this chapter very much, right? So you can say that it's a requirement that in haloalkanes, haloarenes, we should have knowledge of optical isomerism. Now, here question is, in SN1 reaction on chiral center, which thing happens, right? So we have seen that, we studied that, right? In SN2 you have inversion, in SN1 you have resmization, right? But we never have 100% resmization. I told you that in SN1 we do have resmization, but inversion is always more as compared to retention. There will be more inversion as compared to retention. So in this case, of course, answer will be A, right? Because you do not have 100% retention or 100% inversion or 100% resmization. You have partial resmization, you can say. And again, this question we got in AIPMT 2015. Now, point is, we have done alkyl halide, its preparation, its property, physical property and chemical property. So after haloalkanes, right, now we have to talk about aryl halide or haloarenes. But as compared to haloalkanes, in haloarenes part, the reactions, the amount of reactions is low, right, in the preparation part also and in the reaction part also. And some of the reactions are very common, which you repeat in almost every chapter, especially that electrophilic substitution reaction, right? So I hope you all know the structure of aryl halides, right? Aryl halides, mainly we take benzene. So with benzene, if a halogen is attached, like fluorine, chlorine, bromine, iodine, right? So they are called aryl halides here. Now, if you talk about its preparation, so its first preparation is from electrophilic substitution reaction. I think electrophilic substitution reaction, you people first discuss in the hydrocarbon chapter, right? In hydrocarbon, we have benzene, and in the chemical properties of benzene, this is the most important reaction, electrophilic substitution, right? Electrophile will come, it will replace the H plus from the benzene carbon, and electrophile will be attached. So point is, if I take a benzene and I have to prepare aryl halide using electrophilic substitution, so here I will have to use X plus electrophile like Cl plus Br plus, right? And those X plus or those Cl plus Br plus, they are unstable, they do not exist. So we need some reagent which can produce those electrophiles, right? Like suppose if I have to prepare chlorobenzene. So to prepare chlorobenzene, what I will do, I will take chlorine, which is non-polar, but to polarize it, I can use AlCl3 or some other metal or some other Lewis acid. You know what happens here? This AlCl3 will polarize your chlorine. The chlorine you have, right, in the presence of AlCl3, which is a Lewis acid. Lewis acid has a characteristic to absorb nucleophile and release electrophile. So that AlCl3 particularly, it will break Cl2 into Cl minus and Cl plus. The Cl plus will remain as it is, and this Cl minus, it will attach with your AlCl3. So point is, when I use Cl2 AlCl3, so that will generate Cl plus electrophile, and that Cl plus electrophile will simply attach with the benzene to produce chlorobenzene, right? And I hope you people do know the mechanism here. It's just a two-step mechanism, right? Just a two-step mechanism, right? You have your benzene, which has of course 3 pi bonds in it. From Cl2 AlCl3 reagent, you got this Cl plus electrophile. Just like your alkene, alcohol, benzene also loves electrophile, students. So what it will do, it will share its pi bond with this electrophile. Now point is, pi bond is present between these two carbon. So if you attach chlorine here, so on the other carbon you will get a carbocation, right? So when that pi bond will be completely shared by the chlorine, suppose chlorine is getting attached on this carbon, so a positive charge will be created. So it's like a carbocation, but we call it arenium ion. We call it arenium ion. So that's the first step. Electrophile will attach with benzene, right? A cation will be created. And in the second step, right, to gain its aromaticity, you will see a hyperconjugation here. The carbon at which electrophile has been attached, from the same carbon, a CH bond will be attracted by the carbocation through hyperconjugation, or this is called deprotonation. So finally, your benzene ring will be reformed and a chlorine will be attached here. And from the same carbon, you will notice that one H plus is getting released. So Cl plus electrophile is replacing the H plus electrophile. That's why we call it electrophilic substitution reaction. So using electrophilic substitution, you can prepare chlorobenzene. Not only that, in the similar way, you can also prepare bromobenzene. Like suppose if I take benzene and I take certain reagent which can generate Br plus electrophile. So Br plus can be generated easily by taking Br2 with Fe or FeBr3, right? Fe or FeBr3 will do the same thing that AlCl3 was doing for Cl2. This Fe or FeBr3 will polarize Br2 into Br plus Br minus. Br minus will be taken by the FeBr3, and again Br plus will react with your benzene to produce bromobenzene. Bromobenzene, right? And It's a simple electrophilic substitution reaction of benzene, right? Simple benzene. Sometimes this electrophilic substitution reaction, students, it can happen for substituted benzene also, right? I hope you know that with your benzene, if you have a electron donating group or ortho para directing group, right? Most of the time electron donating groups are ortho para directing, except few cases, right? There is some case in which electron withdrawing group also acts as ortho para directing, and that's the case of halogen itself, right? But most of the time, if you have electron donating groups like OH, alkyl, amine, alkoxide, right? So in these cases, when you do electrophilic substitution, suppose you have an electron donating group and you are putting the same reagent here, Br2Fe. So in this case, again, you will have electrophilic aromatic substitution reaction, but because this group is ortho para directing, so in that case, Br plus will be substituted at para position and ortho position, right? And of course, most of the time para will be major because ortho has more steric hindrance. So not only simple benzene, but benzene derivatives, right, can also go through ES reaction, right? And if you have electron withdrawing group, which is mostly meta directing, like aldehyde, cyanide, nitro, right, carboxylic acid. So in those cases, the upcoming electrophile will be added on meta position. See, halogen is the only case in which it's an electron withdrawing group. Overall, it deactivates benzene. But still the upcoming electrophile goes on ortho or para position. So let me give you one reaction at least for that. Suppose you have this, means you have a benzene on which already a chlorine is attached. And for this chlorobenzene, now you are doing electrophilic substitution reaction. So again, this Cl2AlCl3 will give you Cl plus, right? And this Cl plus can attach on ortho or para position, but again para will be the major product here. Para will be the major product, right? So my point is, this chlorine, it will deactivate. It acts as an electron withdrawing group with benzene, but still it is a ortho para directing group because of its resonance, right? So that's how you can prepare from benzene or benzene derivative your aryl halide. That's our first preparation method. Now let's see a very famous preparation method of aryl halide, which is a name reaction again and known as Sand-Meyer's reaction. In Sand-Meyer's reaction, what we do, we take the very famous reagent or substrate of organic chemistry, which is disonium salt, benzene N2Cl, disonium salt, and we treat that with Cu2X2, where your X can be chlorine or bromine, right? So when you treat that with Cu2X2, you get X on the benzene ring, and this N2 will be released and the chloride will combine with the copper ion, right? And the mechanism of this reaction is very easy, students. If you look at disonium salt, if you look at the structure of disonium salt, so it is something like this in detail. And here N2 is a very good leaving group. So when you add Cu2X2, so Cu2X2 can give X minus ion, which is a nucleophile again, and it can attack on this carbon, right, releasing the N2 group, because N2 is a very good leaving group. N2 has almost inert nature. We have seen that in the inorganic chemistry. So that X minus from Cu2X2 can attack on carbon. You get X and benzene, N2 will go out. And here X can be chlorine, bromine, or sometimes pseudo halides, right? You can use Cu2Cl2, you can use Cu2Br2, and you can use Cu2CN2. Right? In the inorganic P block, we talk about this, that cyanide is a pseudo halide. So when I use Cu2Cl2, I will get chlorobenzene. When I use Cu2Br2, I will get bromobenzene. When I use Cu2CN2, I will get cyanobenzene. But Sandmeyer's reaction is a very famous name reaction for the preparation of aryl halide, right? So you should know that we can prepare aryl halide by Sandmeyer's reaction and electrophilic substitution reaction of benzene. Now, after the preparation of aryl halide, which is of course very, very low, in the physical property part of your aryl halide, right, nothing is much more important, but there is a point which can be asked in the examination. Students, for a di-substituted benzene, we have a comparison of melting point, right? Like suppose if you take para-dichlorobenzene, right? If you take ortho-dichlorobenzene, and if you talk about meta-dichlorobenzene, right? So let me say that this is 1, this is 2, this is 3. Now for this 1, 2, 3, of course these are position isomers. For these position isomers, if I have to compare melting point, so melting point here, it is compared by symmetry and packing in solid state, right? Because why we are talking about this point? Because when it comes to boiling point and melting point, mostly in our mind it comes like number of carbon, molar mass, size, branching, right? But in case of melting point especially, not in boiling point, but in case of melting point especially, please remember that symmetry or arrangement is a factor, If your molecule is symmetrical, it can have close packing. The molecules can be very close to one another. And when they are very close to one another, they will have a higher intermolecular force. And higher intermolecular force means they will have more melting point. So if you check carefully, the first one is most symmetrical one, right? The para isomer. So for para isomer, the melting point will be highest. Melting point will be highest here for para. And if you compare the ortho and meta isomer, you can notice that in case of meta, because this chlorine is coming in between, right? So when you do packing of one molecule, second, third, fourth molecule, so the separation between molecule will be higher, right? Okay, let me tell you what I am talking here. I am talking about packing means if I take para. So this is a para, this is another para, this is another para, right? So in para, the molecules can be placed very near to each other. They will have very, very low separation. In case of ortho, the separation will increase. The separation will increase. And in case of meta, the separation will be highest. The intermolecular space will be highest. Yeah. So visually you can understand this, that here the separation is very, very low, here separation is little high, and here separation is more. So that's why melting point will be highest for para, then for ortho, and then for meta. And this is important. This is important. They can ask in the exam about the comparison of ortho, meta, para, dihalobenzenes, right? So after this melting point, now let's talk about, students, the reactions of haloarenes. But again, when it comes to reaction, I told you first you need to see that what types of reaction we can have. So just like haloalkanes, in case of haloarenes also, we have 3 types of reaction, right? Here also we have SN reaction. Here also we have reaction with metal. 2 things is common, right? They were also there for all haloalkanes. The only difference is, in case of haloalkanes, we had elimination reaction. So in haloarenes, we do not have elimination. Instead of that, we have electrophilic substitution reaction, which I have already discussed in the preparation just now. So now let's see first the SN reaction of aryl halide. Students, please focus. If you take chlorobenzene, which is an example of aryl halide, and you treat with certain nucleophile, So first point you need to understand here that this reaction under normal condition is not possible. Why? Because for aryl halide or vinyl halide, remember alkyl, allyl, benzyl, aryl, vinyl. So for aryl halide and vinyl halide, SN reactions are difficult. because in both aryl and vinyl halide, right, due to resonance, right, of course this chlorine has lone pair, so it will go into resonance, it will have resonating structure, and in the hybrid structure you will have a partial double bond character. So due to partial double bond character, this carbon chlorine bond, or this in general carbon halogen bond, is very strong, and if this bond is very strong, right, you cannot break this bond easily. So first point here, you need to understand that for aryl halide, SN reactions are difficult. SN reactions are difficult under normal condition. So now forcefully, if you want to do SN reaction, you will have to increase the temperature, pressure, or you will have to see some other ways, right, to do the SN reaction. Now for this aryl halide particularly, there are two ways by which you can perform SN reaction. One is by elevating the temperature, right? Like you take chlorobenzene, you treat with aqueous NaOH, right? And you take high temperature like 623 Kelvin, you take high pressure like 300 atm. So at high pressure, high temperature, it will go through SN reaction, and this is called aromatic nucleophilic substitution, ARSN, right? But after substitution, this OH minus will attack on this chlorine will go out, and eventually you will feel that you will get OH group here, but that's not the case. You should be always careful in the organic reactions. No doubt chlorine will be replaced by the OH group, right? But because phenol is acidic in nature, and you are using a basic medium here, so this H plus will go out. This H plus will be removed automatically. So instead of phenol, you will be getting sodium phenoxide here. If you want phenol, you will have to do further protonation, right? But SN reaction can be performed at extreme condition, high temperature, high pressure. One more way to do SN reaction of aryl halide is by attaching electron withdrawing groups into it, right? Suppose I took chlorobenzene, and with this I have added nitro group, which is a very strong electron withdrawing group. So when you attach electron withdrawing group, right, that will increase the reactivity towards SN reaction, right, or that will decrease the amount of temperature requirement. Like without electron withdrawing group, suppose that if your temperature requirement is 623 Kelvin, so in the presence of electron withdrawing group, now the temperature requirement will be less, round of 300-400 Kelvin. And more electron withdrawing group if you attach, so less amount of temperature you need, right? So if I take this para chloronitrobenzene, and instead of this, if I take this NO2 on all the ortho para position. So of course, out of these two, the second one, the below one, will be more reactive because it has more electron withdrawing group. More electron withdrawing group you have in your aryl halide, more is the reactivity towards SN reaction, right? I think I don't need to write the reaction now. You know that if I treat with a nucleophile, so that nucleophile it will replace the chlorine. If I use aqueous NaOH, so here I will get sodium phenoxide, here also I will get sodium phenoxide, ONA. The main thing you have to see here is, sir, why this NO2 is increasing the reactivity of chlorobenzene towards SN reaction. So the answer lies in the resonance, and the mechanism of SN reaction. Please focus here, all of you. If I have this compound, nitro and chlorine, suppose that I am doing some SN reaction. So during SN reaction, a nucleophile will come, it will attack on this carbon. Now, when this nucleophile attacks on the alpha carbon, immediately your chlorine will not go out. Initially, both the nucleophiles will be attached on the same carbon, right? And this pi bond will break, it will delocalize on this carbon to maintain the valency. So after attack of nucleophile, you will get this kind of species, this kind of intermediate, chlorine and upcoming nucleophile, both will be attached on the same carbon, and this pi bond will be here now as a lone pair, as a negative charge. Rest structure will be same. Now if you notice, this negative charge, this anion, can be stabilized by the nitro group, because when this anion goes here, this pi bond will delocalize here, and on the carbon where we are getting negative charge, on the same carbon we have electron withdrawing group. So that NO2 can stabilize this anion. That means what? That NO2 can stabilize the intermediate that we are getting during nucleophilic substitution. And one thing you know all very well, that if your intermediate has more stability, that means you have more reactivity, right? Similarly, if I add more number of NO2, right, more will be the reactivity of chlorobenzene towards SN reaction. So this point of increasing SN reaction of aryl halide towards SN reaction by adding electron withdrawing group. So from this point again, you can get questions in the examination, right? Now, after SN reaction, the next part, and again the most famous part, is electrophilic substitution. But let me tell you one thing, students. Electrophilic substitution reaction is the most repeated one in all the chapters. Like first you talk about this in your hydrocarbon. For benzene, you talk about 5 electrophilic substitution reactions, right? Alkylation, acylation, nitration, sulfonation, halogenation. Those 5 reactions will be repeated here. The only difference is, in hydrocarbon we had pure benzene, but here we have a benzene derivative, right? So point is, if I take a haloarene like chlorobenzene and I do electrophilic substitution, so we have total 5 electrophilic substitution reaction, right? And we can do that always together to save our time. We don't have to do those reactions one by one, because all those reactions have same concept. Every time you have the same mechanism. Electrophile will come, right? It will attach an ortho para position. Carbocation will be formed, adenine ion will be formed, and later on hyperconjugation. So point is, if I take chlorobenzene and I try to do halogenation, right? So for chlorination, I will take Cl2AlCl3, and for bromination, I will take Br2Fe. So this Cl2AlCl3, it will create what? Cl plus ion, and that Cl plus can attach at ortho and para position. So one product I will get this, and one product I will get this. Again, para will be major because in ortho we have steric hindrance, right? This is the first electrophilic substitution reaction, which is called halogenation. After halogenation, if I talk about the second one, which is nitration. So for nitration, we use HNO3 H2SO4. I hope you should know that HNO3 produces NO2 plus ion by losing OH minus to this H2SO4. And once you get that NO2 plus, again it will attach on ortho para position. So you will be getting what? Ortho product and para product. Again, para will be major, right? Similarly, you can do sulfonation reaction. In sulfonation, SO3 group will be added. SO3 is your electrophile. Sometimes they ask that what electrophile we are using. Like when you talk about chlorination, right? In electrophilic substitution, if you talk about chlorination. So in the chlorination, the electrophile is Cl+. In bromination, electrophile is Br+. In the nitration, electrophile is NO2+. In the sulfonation, electrophile is SO3. So sometimes they ask question directly from what electrophile we are using in that particular electrophilic substitution reaction. Now for sulfonation, commonly we use oleum or H2SO4 with SO3. But what we get? We get ortho product, SO3H, and we get para product, right? And each and every time you have the same mechanism, please notice that. So these three are common ones: halogenation, nitration, and sulfonation. Then we have two more, which are Friedel-Crafts reactions, right? One is Friedel-Crafts alkylation, in which you take RCl, AlCl3, right? Again, AlCl3 will break RCl, Cl minus will be absorbed by AlCl3, R plus will be generated. R plus will attack on ortho para position. So you get ortho and para product, but again para will be major, right? And finally, the last electrophilic substitution we have is Friedel-Crafts acylation, in which we use RCOCl with AlCl3. Same concept, AlCl3 will absorb the Cl minus, a cation will be created, and that cation will act as electrophile here. So you will be getting again Cl ortho product, and along with that para product. Again para will be major. So these 5 reactions are common. The same electrophilic substitution you saw in hydrocarbon, now you have seen in this. In the upcoming chapters, same electrophilic substitutions like nitration, halogenation, alkylation, acylation, sulfonation, you will see in the aromatic ether, aromatic amine, phenol. Everywhere we have to repeat the same, right? So those 5 reactions, those 5 electrophilic substitution reactions are important for you: halogenation, nitration, sulfonation, alkylation and acylation. For each and every benzene and benzene derivative compounds, those 5 reactions will be there for you, right? Now, the third reaction of aryl halide, it is quite same as haloalkane, same. Even with same metal, we have to do the reaction. One is with sodium metal, right? So point is, when you take an aryl halide and you react with sodium, right? Same thing will happen. Sodium will give electron to this will break, radical will be created, and 2 radicals will join to give you biphenyl. If you remember, Wood's reaction was quite similar to this. Rx plus Na gives Rr. So benzene X plus Na gives benzene, diphenyl, biphenyl, right? Only the name is different. For alkyl halide, you call that Wood's reaction, but for aryl halide, we call it Fittig reaction. Fittig, right? And the very interesting thing is, for alkyl halide, we call it Wood's. For aryl halide, we call it Fittig. And when we have a mixture of alkyl aryl halide, then we call it Wood's Fittig reaction. Suppose that you take an aryl halide and you mix that with alkyl halide. You put sodium. So R radical, phenyl radical will be created. Those two will combine to give you alkyl benzene. But the name of this reaction will be now Wood's Fittig. Right? So you can say like this, that whether it is haloalkane or haloarene, reaction with sodium has the same concept. Radicals will be created and 2 radicals will be joined, right? Now, even the second reaction of aryl halide with metal is with magnesium, right? And for haloalkanes, we have seen it already, that when alkyl halide reacts with magnesium, it produces Grignard reagent. So same thing will happen here, students. When your aryl halide reacts with magnesium, it will give you aromatic Grignard reagent, MgX. And again, if you have aromatic Grignard reagent, right, think like this, C minus Mg plus, right? So at least the reactivity of aryl halide with metal is quite same as reactivity of alkyl halide with metal. So in the revision part, you can combine those two. You can combine reactivity of alkyl halide, aryl halide with metal together. Right? So now we have done all the reactions of aryl halide, but in this chapter you have to focus a little bit on Grignard reagent too. So for Grignard reagent, just remember one thing, that it is RMgX, R minus Mg plus, and always it will react like R minus and Mg plus. One of the very famous reaction for this is, if you add a reagent which has H plus, acid, water, anything. If you add a reagent that has H plus, so this H plus will obviously combine with R minus, because Mg plus H plus, they can't combine, positive, they repel each other. So that can give you what? Alkane. This is one of the very famous reaction of Grignard reagent we have. And the rest of the Grignard reagents reaction you can find in the chapters like alcohol and aldehyde ketone. Right? So we have to focus on Grignard reagent also in this chapter. Right? So now, after the properties of aryl halide, let's see some of the questions. Let's practice some of the questions. And again, because just now I have discussed the preparation and reaction of aryl halide, so you can do these questions by your own now, right? So if you want, pause this video, right? I have bent down, so you can pause it. You can see the question clearly, right? And later on you can match the answer. So first question is, the following reaction method is not suitable for the preparation of corresponding haloarene products due to high reactivity of halogen. Okay, so point is, we have seen that by electrophilic substitution reaction we can prepare haloarene, but which halogen is not preferred? Of course it will be fluorine, and this point we have seen even in the free radical halogenation reaction of alkane, right? There also fluorine was most reactive, it was explosive, so we never preferred free radical fluorination. So similarly, during the electrophilic substitution also we never prefer, right, direct fluorination. Direct fluorination we never prefer in the electrophilic substitution reaction. So of course the answer will be A. And this question we got in NEET 2024. It's a direct question. We don't have to solve anything, right? Just by reading the question you can give the answer, right? Now the next question is from reaction, I guess. Identify X. Now one by one, your substrate here is aryl halide, but in your benzene you have two halogens. One is bromine, one is chlorine, and you are treating this with Mg. So point is, both ClBr can interact with Mg, but we are taking only 1 mole of both. So out of these two halogen, only one will react, right? And you know very well that when your aryl halide or alkyl halide reacts with metal, right? So this bond has to break. The CCl bond has to break. So if your CCl bond is weak, it can be easily broken, right? So out of CCl and CBr, you know very well that CBr bond is weaker, right? So if only one halogen has to react, so that will be bromine here, because carbon bromine bond is weak. So here it will break, right? And it will produce what? Grignard reagent, something like this. Chlorine part will remain as it is, and here you will have minus Mg plus and Br. So this is your Grignard reagent as intermediate. Now you are treating that with D2O, heavy water. So see, never get confused by D2O. D2O will react same like water. Like in H2O you have H plus OH minus. So in D2O you have D plus and OD minus, right? So you have D plus, you have OD minus in your water, in your heavy water. So this C minus, it cannot combine with OD minus. So this C minus will combine with your deuterium, and it can produce what? Benzene, chlorine, and here you will have deuterium. So now if you check, in the first option we have the case, chlorine and deuterium. So of course the answer will be 1. And if you see the logic of this question, so it is based on the reactivity of alkyl halide towards metal, right? And how D2O reacts. It gives you D plus and OD minus, just like water. Water gives you H plus OH minus after dissociation. So in this case, the answer will be of course 1. And again, this question we got in NEET 2023, right? And these questions are direct, right? Whatever things I have discussed with you, if you have noted down that, right, you can do these questions easily. Now let's see the next one. The compound C7H8. So C7H8, 7 carbon, 8 hydrogen. See, if your compound has 6 or more carbon and number of carbon hydrogens are almost equal, 6, 7, 7, 8, 7, 9, you need to think like this, that it will have a benzene ring in it, definitely. So C7H8, definitely it will have a benzene ring which has 6 carbon. So total 7 carbon is there. So 1 carbon will be outside, like CS3. So this is your C7H8. Undergo the following reaction, the product C. So first we are doing, okay, this is free radical chlorination, right? You know that chlorine heat or chlorine sunlight will do free radical chlorination. So if you do free radical chlorination here 3 times, trichlorination, so in the benzene ring, all the carbons are sp2 and this is sp3 carbon. During the chlorination, free radical chlorination, I told you that always chlorination is preferred on sp3 carbon because it is more electron rich. It is less electronegative. Now this carbon has 3 hydrogen. So when you do 3 times chlorination, all those hydrogens will be replaced and your product will be benzene CCl3. Now CCl3 students, it's a very strong electron withdrawing or deactivating group. Also it's a meta directing group, right? CCl3, CN, NO2, CHO, ketone, right? Carboxylic acid, all these groups are meta directing. Now this is our A. Now this A is treated with Br2Fe. This is nothing but electrophilic substitution of Br plus. So on this, if you treat Br2Fe, so Br2Fe will give you Br plus and it is a meta directing, so Br plus will attach on CCl3 meta position, right? This is our B. And now you are treating with zinc HCl, metal acid. You should know that metal acid is a reducing agent. Metal acid is a reducing agent, right? And metal acid is used to reduce alkyl halide. Metal acid is used to reduce alkyl halide. So this alkyl halide CCl3 will be reduced into simply CH3 again, and you have a bromine here. So that will be your final product, that is C. So it is nothing but metabromotoluene. Metabromotoluene, yes, metabromotoluene. A will be the answer. It's a very simple conversion question, and of course answer will be A. And this question we got again, it's a PYQ, we got in NEET 2018. Right? So now you are understanding very well that what type of question we get from this alkyl halide or aryl halide chapter in our NEET examination, right? Now, can you do this one, all of you? It's a very interesting question. Many people do not discuss this, that sometimes during the substitution reaction on aryl halide, benzyne formation takes place. It's a question of benzyne formation. Just read the question carefully once. Identify A and predict the type of reaction. So if you notice in this question, students, this is our substrate, benzene. Here we have a methoxy group and here we have bromine, and we are treating with NaNH2. NaNH2 is called sodamide and it is a very strong base. It is a very strong base. You must have seen NaNH2 in the double eliminations of vicinal dihalide in the preparation of alkyne in hydrocarbon. In hydrocarbon, in the preparation of alkyne, we use that NaNH2 to do double elimination because it's a strong base. So in this case, what it will do beta elimination from sp2 carbon, right? This is sp2 carbon, this is sp2 carbon, here we have bromine on alpha carbon and this is my hydrogen. So it will do beta elimination. It will remove alpha bromine from this alpha carbon and this hydrogen from beta carbon, right? And it will produce this sort of structure, OCH3, triple bond, and this. Now you can think by your own also that this is highly unstable. This is highly unstable, right? Because in this cyclic ring, you can't have triple bond here. You can't have sp hybridization here. But this intermediate is called as benzyne. This is called benzyne. This is called benzyne. So of course it will react further. Now the same NaNH2 here, it will function as a nucleophile. NH2 will function as a nucleophile. So there is a two possibility. There is a two possibility. This NH2 minus can be added on this carbon as well as this carbon. So you can get two product here, right? Either NH2 will be added on ortho position or at meta position. You won't get para product here, right? So now if you check the answer, right, you can get this product, you can get this product, but it's not elimination addition reaction, it's a substitution reaction. It's a substitution reaction. Overall, if you notice, in this reaction what is happening, this bromine is getting substituted by NH2, right? Bromine is going out and NH2 is coming in, right? But the position is not same, right? Bromine was initially at meta, right? But NH2 can be at ortho and meta, right? So of course in this case our answer will be second one. That means we are getting this product by the substitution reaction, right? So this benzene formation, right? And with benzene formation, how substitution takes place, you should have at least idea of it, right? There is a high chance that you will not get that in the NEET examination, but you should have an idea for this, right? But we got it in the NEET 2017 examination, almost 10 years back. But still there is a probability that they can repeat these questions in the upcoming NEET examination. So benzene formation you should know very well, right? Now, can you do this one, all of you? Which goes through SN reaction most readily? Okay, it's not SN1, SN2, it's a SN reaction of your aryl halide, because all the halogens are attached with benzene ring, right? So in your aryl halide you have seen that SN reaction will be faster if it is attached with extra electron withdrawing group. So OCS3 is a donating group. Here we don't have any group. Methyl is electron donating group, but NO2 is electron withdrawing group, right? So of course here the answer will be third one, because in third we have electron withdrawing group, which will increase the reactivity of aryl halide towards SN reaction. And this question again we got in AIPMT 2011, but these types of questions again you can expect in the upcoming NEET examination, right? Now, we have done the preparations and reactions of alkyl halide, aryl halide, right? But that's not the end of chapter, right? There is a very small point which you should not miss, because sometimes we do get question from that also. Students, in this chapter we have to discuss about certain polyhalogen compounds, right? Especially their structure and uses, right? Like one of the compound is dichloromethane. One of the compound is dichloromethane, CH2Cl2. So if you talk about its usage, so it was used, or it is used as solvent or paint remover, or in metal cleaning and finishing, right? But it is harmful for human. For us it is harmful. We should not come in direct contact with this compound, because it can harm the central nervous system, right? And it can cause hearing and vision problems, right? Sometimes if it comes in contact of your eyes directly, so it can destroy your cornea, right? But for dichloromethane, what is its use, and how it is harmful for us, we should have knowledge regarding this. Similarly, we have another compound like chloroform. You know chloroform very well. In organic reactions also, as a reagent you use chloroform. Reactions like Rimmer-Timman or carbylamine reaction. But chloroform CHCl3, it has a main purpose of creation of freons, right? Freons you know very well, chlorofluorocarbon. So chlorofluorocarbons can be generated by chloroform, and previously it was used as anesthesia in medical, right? Before surgery, like we used to give the patient chloroform, right? But nowadays we don't use that, because there is a very dangerous reaction of chloroform. You know what? Chloroform, if it oxidized, if it reacts with oxygen, it can produce COCl2. It can produce COCl2, which is a very poisonous gas. It is called as phosgene. So that's why nowadays we don't use chloroform now. We use other methods for anesthesia. And another compound in polyhalogen is important, which is DDT, right? DDT, its structure is very important, and its structure you can memorize by its name. Its name is dichloro diphenyl trichloroethane. So see, dichloro, 2 chlorine, diphenyl, 2 benzene, trichloro, 3 chlorine, and ethane means 2 carbon in the open chain, And I hope you know very well that DDT was a very famous insecticide, right? But nowadays in many countries this DDT has been banned, right? We don't use that, because you people know very well that it comes in your food cycle, right? So after this polyhalogen compound and the preparations and reactions of alkyl halide, aryl halide, now I can say that we have done this chapter, and we have to focus on mechanism of all the reactions if possible. Whenever you study organic reaction, please focus on the mechanism, right? And if you talk about the most important reactions in this chapter, so in the preparation part, the free radical halogenation of alkane, the electrophilic addition reactions of alkyne, right, and the Schwarz and Finkelstein reaction. These are very important, right? The preparation of alkyl halide from alcohol, right? I am not writing it here because that reaction you will also see in the alcohol chapter in very detail, right? So in this chapter, you need to focus at least on these three in the preparation of alkyl halide: free radical halogenation, addition, Schwarz and Finkelstein. And then of course, in the preparation of aryl halide, you have to focus on Sandmeier's reaction, right? And the electrophilic substitution, it's a very common, so you will always remember that. So main focus will be Sandmeier's. And in the properties part, SN reactions of alkyl halide, aryl halide, right? Elimination reactions of alkyl halide, its mechanism, E1, E2, deciding E1, E2, SN1, SN2 according to their condition, the activities in SN1, SN2, E1, E2, they are important. And then for both alkyl aryl halide, you know that you have reaction with metal. And then again we have to repeat electrophilic substitution, electrophilic aromatic substitution for haloarenes, and finally we have to end this chapter with polyhalogen compounds. So now I have tried to discuss each and every concept in this chapter in this video. I have touched each and every point that is present in this chapter for NEET examination. Now your task will be to practice as many questions as you can, right? Like in the organic, when you solve questions, so you should not take much time, right? Within 2 minutes, you can solve each and every question. Some questions can be solved in 10 seconds, in 5 seconds, like that. So in organic chemistry, in each and every chapter, you should practice at least 100, 200 questions, right? And some of the questions again we are providing in the description, right? See the description of this video. There you can find the DPPs, and again those DPPs you can find on the PW app. So download PW app, download those DPPs, not only from chemistry, not only for this chapter, right? For rest of the chapters of chemistry, for rest of the subjects also you can get the DPPs if you download the PW app, right? So this is from my side in this video, in this chapter. Thank you so much. Now I will meet in the next video of next chapter's one shot. Thank you so much. Bye-bye.